Every person who has ever lived, every empire that's risen and fallen, every story ever told, it's all happened right here, on a cosmic vessel we call Earth. We are all passengers on this ship, hurtling through a vast stellar ocean at speeds we can barely imagine. Our solar system is just a tiny, forgotten speck in an ocean of stars so vast that our most ambitious dreams are dwarfed by its sheer scale. What if I told you that leaving our home galaxy, the Milky Way, might be one dream that can never come true? Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This isn't a story about failure. It's a story about perspective. It's a journey to the very edge of what humans can achieve, a confrontation with the mind-boggling size of our universe. To get why leaving our galaxy is so profoundly difficult, we first need to figure out where we are inside it. We have to map our cosmic neighborhood before we can even think about moving out. So, let's start that journey not through space, but through scale. We'll begin with a simple question: where in the Milky Way are we? By the end, you'll understand why that question is the key to unlocking one of the greatest challenges humanity might ever face. Our place in a sea of stars. Imagine looking up at the night sky on a perfectly clear night. That glowing, hazy band of stars stretching across the heavens, the one ancient cultures saw as a river of milk, is our home. But what you're seeing is just a tiny sliver of our cosmic city, a massive, swirling metropolis of stars that we're living right inside of. Our galaxy, the Milky Way, is a colossal structure. It's a barred spiral galaxy, meaning it has a bright, stretched-out bar of stars at its center, with majestic spiral arms wrapping around it like water swirling down a drain. Inside this structure are an estimated 100 to 400 billion stars. Each one is a potential sun, and many have their own families of planets. The whole galaxy stretches about 100,000 light-years from one end to the other. To give you a sense of that number, a single light-year is the distance light travels in a year, about 9.5 trillion kilometers. The trip from Earth to our Sun takes just 8 light minutes. So, a 100,000 light-year diameter is an almost impossibly vast distance. If you could shrink the entire Milky Way down to the size of the continental United States, our whole solar system from the Sun all the way out to Neptune would be smaller than a single grain of sand. And while our galaxy is incredibly wide, it's surprisingly flat. The main disk, where most of the stars live, is only about 1,000 light-years thick. This gives the Milky Way the profile of a giant frisbee, or, as some have put it, a pizza. So where are we in this enormous cosmic pinwheel? Well, we're not in the glamorous, bustling city center. Not even close. Our solar system is located about 25,000 to 27,000 light-years away from the galactic core, which puts us roughly halfway to the galaxy's edge. If you think of the galaxy as a vinyl record, the bright, dense center is the label. The spiral arms are the grooves holding all the music, the stars and nebulae. We're living on a tiny speck of dust in one of those grooves, and it's not even a major one. We're in a minor branch called the Orion Cygnus Spur, a little side street about 300-500 light-years wide that sits between two bigger, more prominent arms, the Sagittarius and Perseus arms. It's a quieter neighborhood out here in the galactic suburbs. But this location, far from being a cosmic backwater, is what many scientists call a Goldilocks spot. Our position in this galactic habitable zone might be a key reason life was able to flourish on Earth. The galactic center is a chaotic and dangerous place. At its heart sits a supermassive black hole, Sagittarius A*, an object with the mass of 4 million suns. The area around it is flooded with intense radiation, and the stars are packed so tightly that their gravitational tugs could easily throw planets out of their orbits. Here in the Orion Spur, we're far enough away to be safe from all that chaos. Yet, we're not so far out that the building blocks of life are hard to come by. The outer edges of the galaxy are poor in heavy elements like carbon, oxygen, and iron, the stuff forged in the hearts of stars that you need to form planets and life. Our position is just right, not too chaotic, not too barren. It's a place where our sun can maintain a stable, nearly circular orbit around the galactic center, a journey that takes about 230 million years to complete, all while we spin at a breathtaking 828,000 kilometers per hour. Curious how we even figured all this out. For a long time, we thought we were at the center of everything. Early astronomers like William Herschel mapped the stars and concluded we were near the middle of the galaxy. They couldn't have known that huge clouds of interstellar dust were blocking their view, creating a cosmic fog that hid the true scale of the Milky Way. It wasn't until 1917 that astronomer Harlow Shapley, by studying the distribution of ancient star clusters, realized they were all huddled in one direction, toward the constellation Sagittarius. This discovery radically shifted our perspective, moving us from the center to the quiet outskirts of our own galaxy. Today, instruments like the European Space Agency's Gaia spacecraft have mapped the positions of over 1 billion stars, confirming our suburban address in the cosmos. So, here we are, on a small planet, orbiting an average star, in a minor spiral arm, halfway out from a chaotic center we can't even see properly. We are safe, stable, and alive. But this cosmic geography also hands us our greatest challenge. Our galaxy is our home, our cradle, but it might also be our prison. And as we zoom out, we can start to see the bars. The problem: the tyranny of distance. The human drive to explore is written in our DNA. From our first steps out of Africa, we've crossed continents, oceans, and even left our planet to walk on the moon. Our robotic messengers have gone even further. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object from Earth. As of early 2026, it's about 24.4 billion kilometers, or roughly 15 billion miles away, traveling at a blistering speed of about 61,200 kilometers per hour. And yet, after nearly 50 years of non-stop travel, Voyager 1 has only covered a distance of about 23 light hours. Not light days, or light months. Light hours. To travel just one single light year at that speed would take it around 18,000 years. Let that sink in. 18,000 years for one light year. Now, let's talk about leaving the Milky Way. Our galaxy is about 1,000 light years thick. To get out, we don't have to cross the whole 100,000 light-year diameter. We just have to travel up or down out of the galactic disk. From where we are, that's a trip of about 500 light-years to the edge. Using our fastest deep space probe, Voyager 1, as a benchmark, that 500 light-year journey would take 9 million years. To put that in perspective, modern humans have only existed for about 300,000 years. This journey would take 30 times longer than our entire species has been on this planet. But let's be optimistic. Let's imagine we could build something way faster. The Parker Solar Probe is technically our fastest spacecraft, but it only hits its incredible top speed for brief moments as it slingshots around the sun, so it's not suited for a long-haul journey. Let's dream up a ship that could travel at 1% of the speed of light. That's a mind-boggling 3,000 kilometers per second. Even with this incredible speed, the journey out of the Milky Way would take 50,000 years. 50,000 years of continuous travel, just to pop our heads out of the galactic disk and wave goodbye. This is the tyranny of distance. The numbers are so big they almost lose their meaning. We think of a trip to Mars, which takes months, as a monumental task. The 73,000-year trip to our nearest neighboring star system, Proxima Centauri, with today's technology seems like pure fantasy. A trip out of the galaxy is orders of magnitude beyond even that. And what would we find if we got there? Intergalactic space. The void between galaxies. The nearest major galaxy to ours is Andromeda. It's a beautiful spiral, even bigger than the Milky Way. It's also hurtling toward us at about 110 kilometers per second, set for a cosmic collision in about 4-5 billion years. But right now, it is 2-5 million light-years away. Let's go back to our ship traveling at 1% the speed of light. To cross the gulf to Andromeda would take that vessel 250 million years. During that time, the continents on Earth would have shifted into unrecognizable shapes. Entire mountain ranges would have risen and eroded to dust. The journey is longer than the entire time dinosaurs walked the Earth. This is the fundamental problem. Space isn't just big, it's a profound emptiness, with islands of matter so far apart that the distance itself becomes a physical barrier more formidable than any wall. The energy required to cross these voids is staggering, and even if we could achieve it, the journey itself is filled with dangers that go far beyond loneliness. Distance is the first great filter, but it's far from the last. The problem: the perils of the journey. Let's pretend for a minute we solve the distance problem. Let's say we invent a propulsion system that can get a ship moving at a real fraction of the speed of light. We have a crew of brave pioneers ready for a journey of millions of years, maybe in a generation ship or cryosleep. Even then, the universe itself becomes the enemy. The void isn't truly empty, it's a treacherous ocean of invisible hazards. The first and most relentless of these is radiation. Here on Earth, we're protected by a double-layered shield, our planet's magnetic field and its atmosphere. Together, they stop the vast majority of harmful radiation from the sun and deep space. But once you leave this bubble, you are exposed to the full, unfiltered fury of the cosmos. There are two main types to worry about. First are solar particle events, massive bursts of energy thrown off by the sun. A big one could deliver a lethal dose of radiation to an unshielded astronaut in hours. A ship could be hardened against this, but the real monster is the second type, galactic cosmic rays, or GCRs. GCRs are the hearts of atoms' protons, helium, even iron that have been shot across the universe by distant exploding stars and other violent events, accelerated to nearly the speed of light. These aren't like medical X-rays. They are tiny, relativistic cannonballs that tear through everything they hit, including spacecraft hulls and human bodies. They slice through DNA, dramatically increasing cancer risk over long journeys. They can damage the central nervous system, leading to cognitive decline and memory loss, a disaster for a mission that depends on complex problem solving. They can also cause degenerative effects on the heart and accelerate conditions like cataracts. Shielding against GCRs is a monumental challenge. Unlike low-energy radiation, which can be stopped by lead, high-energy GCRs hitting a dense material can create a secondary spray of even more radiation, making things worse. The best shield seems to be things with light nuclei, like water or liquid hydrogen. But to provide enough protection for a journey lasting millennia, a spacecraft might need a shield of water several meters thick, adding an impossible amount of weight to the ship. A mission to Mars could expose an astronaut to radiation equal to hundreds of CT scans. A journey through intergalactic space would be orders of magnitude worse. Beyond radiation, there's the physical threat of micrometeoroids. Space is filled with tiny grains of dust and rock. At normal speeds in our solar system, they're a manageable risk. But when your ship is traveling at, say, 10% the speed of light, the energy of even a sand-sized grain becomes catastrophic. A 1-gram particle hitting a ship at that speed would have the explosive power of over 10 tons of TNT. A collision with a pebble would vaporize the ship instantly. How do you shield against that? A physical shield thick enough would be too heavy to even get moving. A laser defense system would need to spot and vaporize trillions of particles from miles away, every second, for thousands of years, without fail. Finally, there are the challenges for the crew themselves. Long-term exposure to zero gravity causes muscles to waste away and bones to lose density. Fluids shift into the head, putting pressure on the eyes and causing vision problems. While a rotating habitat could simulate gravity, the psychological toll is harder to solve. Imagine being confined to the same ship, with the same people, for your entire life, knowing your children and their children will live and die within its walls. Earth would shrink to a dot of light, then disappear entirely. You'd be adrift in a blackness so complete and unchanging it could break the human spirit. So, the problem isn't just one of distance. It's a tangle of interlocking challenges. To leave the Milky Way, you need a ship that can go impossibly fast, survive a constant barrage of radiation and impacts, and house a crew that can survive for a time span that dwarfs all of human history. The dream of leaving our galaxy requires us to conquer the very laws of physics and biology. The solutions? Propulsion dreams. Faced with such massive challenges, it's easy to feel a little cosmic despair. But humanity's story has always been about facing the impossible and dreaming up solutions. The dream of interstellar travel has inspired some of the most brilliant and out-there ideas in science. We can't build them today, but they are the theoretical paths that might one day lead us to the stars. The slow boat, generation ships and cryosleep. The most straightforward approach, the one that relies on the least amount of new physics, is the slow boat. This idea accepts the immense travel times and just tries to outlast them. A generation ship is maybe the most romantic and tragic of these ideas. It would be a self-contained world, a massive ark carrying a community of thousands on a one-way trip. This ship would need a perfectly closed ecosystem, recycling every drop of water, every molecule of air, and every nutrient for hundreds of generations. The people who boarded would know that neither they, nor their children, nor their great-grandchildren for 100 generations, would ever see the destination. Their lives would be dedicated to the journey itself, a multi-millennial act of faith. A more popular science fiction alternative is cryosleep. The idea is simple: if the journey is too long for a human lifespan, just pause the lifespan. By lowering an astronaut's body temperature, their metabolism could be slowed to a near standstill, letting them sleep through the centuries. This isn't pure fantasy. A medical practice called therapeutic hypothermia is already used to slow metabolic rates in patients. However, true cryogenic freezing is currently a one-way trip. When water freezes, it forms sharp ice crystals that would shred every cell in the body. To stop this, we'd need to replace the water in the body with a kind of biological antifreeze. But we have no idea how to do this safely in a human, let alone how to reverse it without causing catastrophic damage. And even if we could, who would maintain the ship?
What automated system could run flawlessly for 1,000,000 years to protect the sleeping crew? The brute force method, nuclear propulsion. If you want to go faster, you need more power. A lot more. In the 1950s and 60s, a team of physicists, including Freeman Dyson, worked on a top-secret program called Project Orion. The idea was to propel a ship with a series of nuclear explosions. The ship would drop small atomic bombs out its back, which would detonate a short distance away. The blast would hit a massive pusher plate, which was mounted on giant shock absorbers. It was, essentially, a ship that would ride a staircase of nuclear fireballs into space. The physics was sound, and an Orion drive could have potentially accelerated a ship to 5% the speed of light. However, the project was cancelled, partly due to the treaty that banned nuclear explosions in space. A more advanced concept was Project Daedalus from the 1970s. This was a design for an uncrewed probe to reach a nearby star within 50 years. Instead of crude bombs, it would use a more controlled form of nuclear fusion. The engine would shoot tiny pellets of fuel into a chamber and zap them with powerful beams 250 times a second. Each zap would trigger a micro-fusion explosion, creating a relentless stream of thrust that would accelerate the probe to an incredible 12% the speed of light. Though never built, Daedalus proved that interstellar travel within a human lifetime was, in principle, possible. The ultimate fuel, antimatter engines. For the ultimate in propulsion, we have to turn to the most energy-dense substance allowed by physics, antimatter. When matter meets antimatter, they annihilate each other, converting 100% of their mass into pure energy. A theoretical antimatter-powered ship could reach speeds of over 50% the speed of light, making a trip to Proxima Centauri possible in under a decade. But the challenges are almost beyond imagination. First, antimatter has to be created, particle by particle, in giant accelerators like those at CERN. The total amount of antimatter ever created by humanity is measured in nanograms. The cost is astronomical, estimated at trillions of dollars per milligram. Second, you can't just put antimatter in a bottle, it would instantly annihilate on contact. It would have to be suspended in a perfect vacuum by powerful magnetic fields, an unbelievably complex and fragile system. Bending the rules, warp drives and wormholes. What if, instead of trying to travel through space, we could travel with space? This is the idea behind the most speculative, yet tempting, form of travel, the asterisk warp drive. Popularized by Star Trek, the concept was given a mathematical foundation in 1994 by physicist Miguel Alcubierre. An Alcubierre drive would warp spacetime itself. A ship would sit inside a warp bubble, while the drive compressed spacetime in front of it and expanded spacetime behind it. The ship would ride this wave, potentially arriving at its destination faster than a beam of light traveling outside the bubble. It's an elegant idea, but it comes with a huge catch. It requires exotic matter with negative energy. This is a hypothetical substance that would have anti-gravitational properties. While some quantum effects suggest negative energy might exist on a tiny scale, we have no idea if we can create it in the amounts needed. Alcubierre's original math required a Jupiter-sized mass of it, and while newer theories have reduced that amount, it still remains in the realm of science fiction. These ideas show us that the path to the stars isn't one single road, but a branching tree of incredible concepts. Each one requires a leap in technology and resources as vast as the distances they seek to conquer. And underlying them all is the single, unifying currency of the cosmos: energy. The ultimate barrier: energy. We've dreamed of incredible ships powered by fusion and antimatter, but there is a final, brutal reality check that underpins all of it: energy. The amount of energy needed for intergalactic travel is so vast that it redefines what impossible means. Let's start with Project Daedalus, the fusion probe. To get it up to 12% of the speed of light, the total energy released would be equivalent to hundreds of thousands of times the world's entire energy consumption for a year. We're not talking about building a new power plant, we're talking about harnessing a huge fraction of the entire energy output of human civilization over centuries, just for one uncrewed probe. And Daedalus was a flyby mission. It didn't need to slow down. If you want to send humans and actually stop, the ship has to burn just as much fuel to decelerate as it did to accelerate. This is the cruel tyranny of the rocket equation. Now, let's consider antimatter. According to NASA, making 1 gram of antimatter with today's technology would require roughly 25 million billion kilowatt-hours of energy. The entire world's electricity production is about 27,000 billion kilowatt-hours per year. So, to produce a single gram of antimatter, we'd need to dedicate the entire electrical output of the planet for nearly 1,000 years. A crude mission to a nearby star would likely require tons of it. The energy cost to produce that much fuel is beyond civilization scale. It would require something like a Dyson sphere, a megastructure that surrounds a star to capture all its energy. We'd need to harness the full power of our sun and a warp drive? Even if we could create negative energy, the sheer magnitude of the spacetime distortion would be immense, calling for astronomical energies. This is the ultimate barrier. It's not just a technological hurdle, it's a fundamental energy limit. Leaving our solar system requires civilization-scale energy. Leaving our galaxy requires stellar-scale energy. We are a species that still largely relies on burning fossilized plants to power our world. The gap between our current capabilities and the energy demands of interstellar travel isn't a gap, it's a chasm. To truly leave the Milky Way isn't a task for a nation or a generation. It would require a species to have reached a level of technological mastery that is, for us, indistinguishable from magic. We would need to become a Kardashev Type II civilization, capable of commanding the full power of our star. Only then could we even begin to afford the price of a ticket to another galaxy. Exploring these colossal ideas really stretches the limits of our imagination. If your mind is spinning with these possibilities just like ours, consider subscribing and joining the conversation. Let us know in the comments, which of these propulsion dreams do you find most inspiring? The brute force of Orion, the elegant precision of Daedalus, or the mind-bending physics of a warp drive? We'd love to hear what you think. So, will humans ever leave the Milky Way? After our journey through the vastness of our galactic home, the tyranny of distance, the perils of the void, and the astronomical energy costs, the honest answer seems to be probably not. At least, not anytime soon, and maybe not ever. The challenges are so profound they seem woven into the fabric of physics itself. We are, in a very real sense, island dwellers. We were born on a beautiful world, but it's an island adrift in an ocean so staggering that the other islands are, for all practical purposes, unreachable. Every star you see in the night sky is part of our own Milky Way. The light from our neighbors, like Andromeda, began its journey millions of years ago, a ghostly reminder of worlds we can see but likely never touch. But to end the story there would be to miss the point. Acknowledging our limits isn't a reason for despair. It's a reason for perspective. The near impossibility of leaving our galaxy doesn't make our existence meaningless. It makes our home infinitely more precious. It highlights the staggering improbability of life, the sheer luck of being on the right planet, in the right solar system, in the right corner of the galaxy for consciousness to wake up and look at the sky and wonder. The dream of intergalactic travel, even if it stays a dream, pushes our science forward. It inspires us to ask bigger questions. The pursuit of fusion rockets could give us clean energy on Earth. Studying long-duration spaceflight teaches us about our own bodies. Contemplating a warp drive pushes the boundaries of physics. Humanity may never set foot in another galaxy. Our destiny may be tied to the fate of this one, but it has always been our relentless, unyielding, and beautiful curiosity that has defined us. And even if we are confined to this one magnificent, sprawling city of stars, there are still up to 400 billion suns to explore, countless worlds to discover, and mysteries to solve right here, in our own galactic backyard. Leaving the Milky Way might be a dream that never comes true. But the act of dreaming it, of striving for it, of doing the science and telling the stories, that is what makes us human. And that is a journey that is always worth taking. Part 2, The Distance Problem. And the bars of that prison begin with something simple: distance. Not danger. Not lack of courage. Not even lack of technology, at least not at first. Before all of that, there is distance. Quiet, patient, and almost impossible to feel properly with the human mind. Because when we say that space is large, what we usually mean is that it sounds large. We hear the numbers, we repeat the words, but deep down, most of us still imagine distance in the way our ancestors did. A road, a sea crossing, a mountain pass. Something difficult, yes, but still something that belongs to the world of journeys. The distance between stars does not belong to that world. And the distance between galaxies feels even less like a journey, and more like a separation between realities. So now that we know where we are inside the Milky Way, the next question becomes much more serious. If human beings ever wanted to leave our galaxy, how far would we actually have to go? What would that number mean in real terms? How long would it take, even in our most optimistic dreams? And what does it reveal about the true scale of the universe around us? That is where this part of the story begins. Because the first step in understanding why humans may never leave the Milky Way is not imagining a starship. It is learning how to sit still for a moment and let the numbers become real. The difficulty is that human intuition was never designed for this. We are creatures of fields, forests, coastlines, and cities. We understand the distance to a nearby shop. We understand the drive between two towns. With a little effort, we can imagine the size of a country, or even the crossing of an ocean. But once distance grows beyond ordinary life, the mind begins to smooth it out. 1,000 kilometers feels big. 10,000 feels bigger. But after a while, all huge numbers start to blur together. Space takes advantage of that weakness. It hides its true scale behind abstraction. A light year sounds almost poetic, until you remember what it is. Light is the fastest thing we know. In empty space, it moves at about 300,000 kilometers every second. Every second. It can circle Earth more than 7 times in that tiny fraction of time. When sunlight leaves the surface of the sun, it reaches Earth in about 8 minutes. That already feels fast enough to belong to another category of reality. Yet a light year is not 8 minutes. It is the distance light travels in an entire year. That is roughly 9.46 trillion kilometers. And the strange thing is, even after saying that out loud, it still does not feel real. Trillion is too large for instinct. The human mind nods politely and moves on. So it helps to build the scale slowly, like stepping stones across a river. The moon, our nearest cosmic neighbor, is close enough that Apollo astronauts could reach it in a matter of days. The sun, by comparison, is much farther away. Not days, but light minutes. The giant outer planets are farther still. By the time sunlight reaches Neptune, the trip takes around 4 hours. And yet even Neptune is still, in cosmic terms, just part of our front yard. That is the first important thing to understand. When people imagine leaving our neighborhood, they often picture escaping the solar system as if that were the major threshold. But the solar system is not the galaxy. Not even remotely. The solar system is a tiny family living inside one ordinary house on one ordinary street in a city so large it almost defeats language. If the Milky Way were shrunk down to the size of North America, our entire solar system would be smaller than dust. And dust does not leave a continent easily. One of the most humbling examples of this is Voyager 1. It is one of humanity's greatest machines, and one of our most moving achievements. It launched in the 20th century, passed the giant planets, and kept going. It is now the most distant human-made object ever sent into space. It has traveled for decades without stopping, moving farther than anything built by human hands has ever gone. And still, in the scale of the galaxy, it has barely begun. In your pasted part 1, that idea is framed beautifully. After nearly half a century of travel, Voyager has covered only about 23 light hours. Not light days. Not light months. Light hours. That detail matters because it pulls the imagination back into reality. Voyager feels far because it is far by human standards. But if we measure it against the stars, it has hardly left the driveway. To travel just 1 light-year at Voyager-like speeds would take around 18,000 years. That is longer than recorded human civilization, longer than agriculture, longer than nearly every monument, empire, language shift, and religious tradition most of us ever learn about in school. A single light year, for one of our bravest machines, is not a voyage. It is almost an era of planetary history. And that should immediately change the emotional texture of the question. Because the nearest star system, Proxima Centauri, is not 1 light-year away. It is more than 4 light-years away. So even the closest star is already a destination so distant that, with present-day spacecraft speeds, the journey would outlast entire civilizations. The ship might still be moving long after the culture that launched it had changed beyond recognition, or vanished entirely. Now let the scale widen again. Leaving the Milky Way does not require crossing the entire width of the galaxy, at least not necessarily. If your only goal were to technically get out of the main galactic disk, the shortest route would not be across the spiral arms. It would be up, or down, out of the disk itself. In the material you pasted, the galaxy's main disk is described as roughly 1,000 light-years thick, which means from our position, a clean exit might still require something like 500 light-years of travel. 500 light-years sounds almost manageable when spoken quickly. But pause on it. 500 light-years is not a nearby region of space. It is not a long mission. It is 500 times the distance light itself travels in a year. At Voyager-like speeds, that becomes millions of years. In your Part 1 text, the estimate comes out to about 9 million years. 9 million years. Modern humans have existed for only a tiny fraction of that time. If you launched such a journey when the earliest humans were first learning to live together in small groups, the craft would still not be out of the Milky Way today. This is where the question begins to change shape. At first, will humans ever leave the Milky Way? Sounds like a challenge of engineering. Build a stronger engine. Build a smarter ship. Be patient. But the more honestly you face the numbers, the more you realize that patience is not the word. These are not just long trips. They are durations so extreme that they threaten the meaning of the word travel itself. Travel implies continuity between departure and arrival, a memory of where you came from, a plan for where you are going, a human relationship between the two. But what is a trip that lasts 50,000 years? What is a journey that outlasts nations, languages, coastlines, religions, and maybe even species? At some point, a trip stops feeling like movement and starts feeling like inheritance. To make this easier to grasp, imagine a hypothetical ship far beyond anything we can build now. Forget Voyager. Forget chemical rockets. Imagine a future vessel that can cruise at 1% of the speed of light. That is already an almost absurd speed by our standards, about 3,000 kilometers every second. At that velocity, the numbers become less hopeless, but only less hopeless in the way a desert becomes less dry after one cloud passes overhead. At 1% light speed, leaving the galactic disk could still take around 50,000 years. That estimate appears in your Part 1 as well, and it lands exactly the way it should, with a kind of soft dread. Because 50,000 years is not a wait. It is not a mission timeline. It is the rise and fall of whole worlds. And even then, what have you actually achieved? You have not reached another galaxy. You have not arrived at some neighboring civilization. You have only just stepped out of the dense stellar disk of your own home galaxy and into a darker, lonelier stretch of space. That is another misconception worth letting go of. Leaving the Milky Way does not mean entering some busy corridor between galaxies, as if the universe were full of nearby destinations once you make it past the edge. The opposite is true. Beyond the familiar structure of our own galaxy lies a deeper emptiness. The stars thin out. The neighborhoods disappear. The dark becomes larger, not smaller. And then there is Andromeda. Andromeda is our nearest major galactic neighbor, and in a way it is the most emotionally important one, because it gives shape to the dream. When people imagine humanity someday crossing between galaxies, they are often imagining Andromeda without even realizing it. Another grand spiral. Another city of stars. Another possible shore. But Andromeda is about 2.5 million light-years away. Again, the number resists feeling. 2.5 million is a figure the mind can read and fail to absorb in the same instant, so it helps to slow it down. If you had that same 1% light speed ship, the one already far beyond our real capabilities, and you pointed it toward Andromeda, the trip would take around 250 million years. That comparison is in your pasted text too, and it works because it is almost geological rather than historical. 250 million years ago, the world itself was different in ways that are hard to emotionally connect to. Continents were arranged differently. The dominant animals were not humans. Entire ecosystems had not yet appeared, or had already disappeared. That is the timescale we are talking about. A human journey to Andromeda at 1% light speed would not merely outlast civilization. It would outlast most of what we emotionally mean when we say Earth history. And this is why the phrase, the distance problem, is not really strong enough. It sounds like a challenge waiting for a clever solution. But the deeper truth is that distance in cosmology is not just a problem. It is a condition of reality. It shapes what kinds of beings can meet, what stories can connect, what dreams remain dreams, and what futures stay separated forever by the structure of spacetime itself. There is something almost heartbreaking about that. We grow up in a world where movement is power. If a place exists, we assume that in principle it can be reached. Maybe not easily, maybe not soon, but eventually. That is how human history has worked on Earth. Mountains were crossed, oceans were crossed, the sky was crossed, the moon was crossed. So it is deeply unsettling to face a scale of distance that does not merely delay us, but may permanently outrun us. Still, this is not a story about despair. It is a story about accuracy. Because once the distances become honest, something else also becomes honest. Our relationship to home. If the stars of the Milky Way are already staggeringly far apart, and the gulf between galaxies is wider still, then our galaxy stops feeling like just a backdrop and starts feeling like a complete world. Not a stepping stone. A world. Vast enough to hold more suns than any human civilization could meaningfully explore for ages beyond counting. Rich enough to contain billions upon billions of possible stories, planets, failures, lifetimes, and wonders. In that light, the dream of leaving the Milky Way becomes stranger. Less like the next step after interstellar travel, and more like the edge of what a species like ours can even hope to imagine without slipping into fantasy. And yet imagination matters here. It matters because measuring the impossible does something valuable to the mind. It makes you see ordinary reality differently. The next time you look at the night sky, you may feel that shift. The stars will still look close, because sight is deceptive. They will still seem scattered on a dark surface, calm and accessible. But now there may be a new feeling beneath that beauty. A sense of scale. A quiet awareness that even the nearest points of light belong to distances that would overpower human lives, human memory, and maybe even human continuity. That awareness does not make the universe colder. In a strange way, it makes it more intimate. Because it reminds us that our home is not small. Our home is immense. We are not trapped in a cramped corner of creation. We are living inside one of its great structures, a spiral of hundreds of billions of stars, with more than enough mystery to humble every generation that will ever live. And still, there is tension here. Because if the distance is this severe before we even begin talking about propulsion, then another question rises almost automatically. Not just how far it is, but how fast we can actually go. Because numbers alone do not close the case. They only set the stage. If the Milky Way is separated from its neighbors by distances that feel almost eternal, then the next thing we have to ask is simple. What is the true speed of humanity? Not our hope, not our fiction, not our future dreams. Our real speed. The speed of the machines we have actually built, and the speed of the ones we can realistically imagine. And once we ask that, the problem becomes even sharper. Because distance is only half the story. The other half is velocity. And if you've enjoyed this slow journey through the scale of the cosmos, you can quietly leave a like, subscribe, or share where in the world you're listening from tonight. I always like seeing how many different corners of Earth are looking up at the same sky. For now, just hold on to this one thought as the stars drift overhead. The Milky Way is not hard to leave because we lack courage. It is hard to leave because the universe is under no obligation to make itself reachable. And in the silence between one galaxy and the next, that truth becomes almost impossible to ignore. Part 3. How fast humans can really travel. If distance is the first wall standing between humanity and the edge of the Milky Way, then speed is the second. And speed, in some ways, is even more deceptive. Because human beings are used to thinking in terms of relative motion. A car feels fast on an empty road. A plane feels fast because it can carry you across a continent in a single day. A rocket feels unimaginably fast because it can leave Earth entirely. So when we hear that our spacecraft travel at tens of thousands of kilometers per hour, it sounds like we have already entered a futuristic age of motion. It sounds like the problem must simply be one of patience. Just keep flying long enough, and eventually the galaxy gives way. But space does not measure speed the way we do. The universe does not care that something seems fast to the human body. It only cares how far that speed actually carries you across a real cosmic distance. And when that comparison is made honestly, the story becomes much quieter and much stranger. Because the truth is that humanity is still moving through the cosmos at a pace that is, on the galactic scale, almost stillness. That can be hard to accept at first. After all, we are not motionless creatures. Earth rotates. Earth orbits the Sun. The Sun orbits the center of the Milky Way. Even sitting in a chair in the middle of the night, completely still, you are part of several motions at once. You are being carried around the Sun at roughly 107,000 kilometers per hour. The Sun itself is carrying you around the galaxy at hundreds of thousands of kilometers per hour. By ordinary standards, you are already moving faster than any road, storm, or aircraft could ever suggest. And yet none of that counts as human travel in the sense that matters here. Because those motions are not chosen by us. They are the default currents of the cosmic sea. We are being carried by the river, not steering across it. The moment humans try to steer, the numbers change dramatically. And that is where the illusion begins to fall apart. To leave Earth, a spacecraft first has to fight gravity. That alone takes an immense amount of energy. Rockets burn huge quantities of fuel just to rise through the atmosphere and climb out of Earth's gravitational well. It is one of the most demanding parts of the whole process. The violence of launch, the roar, the heat, the huge white plume beneath the engine, all of it is really just the price of taking the first step away from home. And even after that first step, a second problem appears. Space is empty, but empty does not mean effortless. Once you are free of Earth, you still remain inside the much larger gravitational territory of the Sun. And beyond that, you remain deep inside the structure of the Milky Way. So when we say a spacecraft is fast, we have to ask a more careful question. Fast compared to what? Fast enough to leave Earth? Fast enough to leave the solar system? Fast enough to cross the gap to another star? Or fast enough to someday slip beyond the galaxy itself? These are very different thresholds, and one of the reasons people underestimate the challenge of interstellar or intergalactic travel is that all of these thresholds are often blended together in the imagination. Leaving Earth feels dramatic, so it quietly gets mistaken for leaving the neighborhood. But the neighborhood is much larger than that. Much, much larger. To see this clearly, it helps to look at the actual machines we have built. Take Voyager 1, one of the most extraordinary objects humans have ever made. It launched in 1977, visited the outer planets, and then continued onward into the dark. It is still sending signals back to Earth from farther away than any other human-made object. In the human story, Voyager 1 is an astonishing success. It is a symbol of ambition, engineering, patience, and continuity. It has survived for decades in conditions no ordinary machine was ever meant to endure. And yet, if we ask the Milky Way what Voyager has accomplished in terms of travel, the answer is humbling. Voyager is moving at around 17 kilometers per second relative to the Sun, or roughly 61,000 kilometers per hour. That sounds blisteringly fast, and by the standards of human life it absolutely is. At that speed, you could circle Earth in less than an hour. At that speed, the distance between major cities becomes trivial. At that speed, the whole map of our species collapses into something tiny. But against the stars, that speed is still painfully small. A single light year is about 9.46 trillion kilometers. So when you place Voyager's speed against that distance, the result is startling. To travel 1 light year would take about 18,000 years. Not 10, not 100, not even 1,000. 18,000 years for 1 light year, and the nearest star system is more than 4 light years away. That means that with something like Voyager's speed, even the nearest star is not a destination for a civilization that thinks in normal historical terms. It is a destination for a continuity so long that it begins to feel more like geology than travel. And Voyager is not slow because our engineers are foolish. It is slow because space is honest. The same is true of New Horizons, the spacecraft that flew past Pluto and gave humanity one of its most beautiful glimpses of the outer solar system. When it launched, it became the fastest spacecraft ever to leave Earth, moving at around 16 kilometers per second relative to Earth. That speed allowed it to cross the enormous distance to Pluto in less than a decade, which is an extraordinary technical achievement. But again, once you compare that speed to the stars rather than the planets, the emotional meaning changes. New Horizons feels swift because the solar system is the only deep scale we have truly touched. Once the stars enter the conversation, even our best machines become patient drifters. Then there is the Parker Solar Probe, which is often described as the fastest human-made object ever built. That statement is true, but like many true statements, it can mislead if heard too quickly. Parker reaches incredible speeds, well over 600,000 kilometers per hour during its closest passes to the Sun. It does this by falling inward through the Sun's gravity, skimming close, and using that motion as part of its mission profile. It is a remarkable achievement of planning and heat shielding and courage by design. But Parker is not a Starship prototype. It is not heading outward on a long straight journey to another star. Its speed is partly a product of where it is falling, not a sign that humanity has solved high-speed deep space travel. It is like watching a stone whip around the bottom of a deep well and saying we now understand how to cross an ocean. The motion is real, the speed is real, but the context matters. And context is everything. Because what humans truly need, if the question is whether we will ever leave the Milky Way, is not a brief burst of record-setting velocity in a special orbit. We need sustained, controllable, outward speed over extreme distances. We need a ship that can keep going, not just one that can momentarily move very fast under special conditions. And that is a much harder thing to create. This is why chemical rockets, as powerful as they are, may already be close to their practical limit for this kind of problem. Chemical propulsion works by throwing mass backward very fast. It is elegant in its own blunt way. Fire becomes motion. Fuel becomes escape. But chemical energy is modest compared to the scale of what interstellar travel would demand. It is enough to launch, enough to orbit, enough to send probes outward, enough to land on the Moon and touch Mars with machines. But it is not enough to make the galaxy feel small. Even if we built bigger rockets, or stacked more stages, or launched from the Moon someday instead of Earth, the underlying issue would remain. Chemical fuel simply does not contain enough energy per unit mass to push large human payloads to anything resembling a meaningful fraction of the speed of light. And that phrase matters more than almost anything else in this discussion. A meaningful fraction of the speed of light. Because that is the real threshold where the conversation begins to change. Light moves at about 300,000 kilometers per second. That is the cosmic speed limit. Nothing with mass can simply accelerate past it. And if our best deep space probes move at something like 17 kilometers per second, then what we are really saying is that our current outward travel is not close to light speed. It is not even remotely close. It is a tiny fraction of 1% of light speed. A whisper of it. This is one of those facts that seems obvious once spoken, but is rarely felt emotionally. We live in an age of advanced technology, so it is natural to imagine that we must at least be somewhere along the road to the stars. But the truth is that we are still standing near the beginning of that road, looking into the distance. To understand how far from that threshold we still are, imagine trying to reach 1% of the speed of light. Not half the speed of light. Not even 10%. Just 1%. That would be about 3,000 kilometers per second. Compared to Voyager's roughly 17 kilometers per second, that is not a modest improvement. It is not an upgraded engine. It is a leap into another category of civilization. It is the difference between a riverboat and a lightning bolt. And yet even at 1% of light speed, as we touched on earlier, the galaxy still refuses to become easy. A trip of 500 light-years out of the galactic disk would still take about 50,000 years. That is what makes this subject so calming and so unsettling at the same time. Every time you imagine a future breakthrough, the universe quietly answers, yes, but look again at the numbers. One of the main reasons speed is so hard to gain in space is energy. Kinetic energy does not rise gently. It rises with the square of speed. Double the speed, and the energy requirement is not doubled. It becomes 4 times as large. Increase speed tenfold, and the energy cost rises 100-fold. So even before relativity enters the picture, speed itself becomes expensive in an unforgiving way. And spacecraft have a cruel habit of needing fuel in order to gain speed, which means that the more speed you want, the more fuel you bring, and the more fuel you bring, the more mass you have to accelerate, which means you need even more fuel. This is the old tyranny of the rocket equation, a phrase that sounds technical but points to something very human. Every solution carries its own weight, sometimes literally. That is why so many of our most successful missions rely on gravity assists. Rather than carrying impossible amounts of propellant, we borrow motion from planets. A spacecraft loops around a world like Jupiter and steals a little of its orbital energy, changing speed and direction without carrying all that energy from home. It is a clever trick, and one of the most beautiful examples of cosmic navigation ever devised. The solar system itself becomes part of the engine, but notice what that means. It means that even our best practical methods for gaining deep space speed still depend heavily on the local architecture of our own solar system. They are not general solutions for free movement across the galaxy. They are elegant ways of using the specific arrangement of planets around our own star. Once you leave that system behind, those assists become fewer, then vanish entirely. And that returns us to a more sobering truth. Human spaceflight, for all its brilliance, is still local. We have sent people to the moon. That remains one of the greatest achievements in history. We have sent robots to Mars, rovers that move across another world and send pictures back through the dark. We have placed spacecraft around Saturn and Jupiter. We have touched comets, landed on asteroids, flown beyond Pluto, and crossed the heliopause, the outer region where the sun's influence begins to give way to interstellar space. But even that boundary, dramatic as it sounds, is not the edge of our true cosmic neighborhood. It is simply the edge of the bubble blown by our own star. And our star is only one among hundreds of billions in this galaxy. So when people casually say that humanity is beginning to move into the stars, there is a sense in which that is true. But it is true in the way a child standing ankle deep in the sea has begun to enter the ocean. The contact is real. The milestone matters. Yet the scale ahead is still almost beyond description. There is also another quiet limitation that matters more for human beings than for machines: a human lifetime. Robotic probes can travel for decades without complaining. They do not age in the emotional way we do. They do not get lonely. They do not need meaning, sleep, community, or a future they can personally reach. But human travel is defined by more than motion. It is defined by the traveler. If a machine takes 40,000 years to arrive somewhere, that is a technical problem. If a human mission takes 40,000 years, that becomes something deeper. It becomes a question of biology, memory, purpose, and inheritance. Even if we had a ship that could safely move much faster than today's probes, the speed would still need to be judged not only against the stars, but against the human heart. How long can a journey remain a journey before it becomes a civilization living inside a machine? How fast must a ship move before the people aboard can still imagine the destination as part of their own lives, rather than as a legend passed forward through generations? These questions do not make the problem less scientific. They make it more complete. Because a spacecraft is not simply an engine with walls around it. If it carries humans, it carries time in a different way. And then, quietly, another subtle difficulty appears. The faster you go, the more dangerous even small things become. A grain of dust floating in space is harmless at ordinary speeds. At a significant fraction of the speed of light, it becomes a projectile of terrifying energy. The emptiness of space is not perfectly empty. There are atoms, particles, grains, radiation, relics of old violence moving silently in the dark. Speed turns them into hazards. So the dream of traveling faster does not simply solve the problem of distance. It creates new problems of shielding, impact, navigation, and survival. That is why speed in the real universe is never just a single number on a dial. It is a whole ecosystem of consequences. There is also relativity, waiting in the background like a deeper layer of reality. As a ship approaches a significant fraction of light speed, time itself begins to behave differently for those aboard compared with those left behind. This idea is often presented in dramatic ways, but at its core it is strangely calm. Motion changes time. The faster you travel, the more your path through the universe reshapes your experience of duration. At very high speeds, this could in principle make long journeys feel shorter for the travelers themselves. But again, the emotional catch arrives quietly. Even if the crew experiences less time, the outside world continues. Home continues. History continues. The stars continue. So relativistic travel does not eliminate distance so much as redistribute its consequences. It helps one clock, while leaving the wider story unchanged. And perhaps that is the deepest lesson in all of this. When humans ask how fast we can travel, we often think we are asking for a number. But we are really asking what kind of beings we are in a universe built like this. Are we coastal explorers, hugging the shoreline of one star system for a very long time? Are we patient builders who may someday send slow arcs between nearby stars? Are we destined to remain, for ages beyond counting, a solar system civilization with ambitious machines but local roots? Or will some future breakthrough change the scale of what movement means? For now, the honest answer is both impressive and humbling. We are fast enough to leave Earth. Fast enough to cross the moon's orbit. fast enough to reach the outer planets with machines, fast enough to send messages and instruments to the edge of the sun's immediate domain. But we are nowhere close to being fast enough for routine travel between stars, let alone between galaxies. Not yet. And there is no shame in that. In fact, there is something strangely beautiful about it. It means we are still in the early chapters, still learning the grammar of motion, still discovering how little our instincts prepared us for a universe this large. If this quiet walk through the numbers is helping you settle in for the night, you can gently leave a like, subscribe, or tell me in the comments where you're listening from. I always enjoy seeing how many places on Earth are connected by the same sky and the same questions. For now, just let one thought settle softly into place. Humanity is not slow because it lacks imagination. Humanity is slow because the cosmos sets a very high price on movement. And before we can seriously ask whether humans will ever leave the Milky Way, we have to become much more precise about what leaving even means. Because escaping Earth is one thing, escaping the solar system is another, escaping the sun's neighborhood is another again, and escaping the galaxy is something else entirely. So the next step in this journey is not just to talk about speed, it is to separate the layers of home. To understand the enormous difference between leaving a planet, leaving a star, and leaving a galaxy. Because until those distances are felt clearly, the Milky Way will keep sounding smaller than it really is. And it is anything but small. Part 4, Leaving Earth, Leaving the Solar System, Leaving the Galaxy. Sometimes the biggest confusion in space begins with a single word. Leaving. It sounds simple, clean, final. As if there is one clear line, and once you cross it, you are truly gone. We say humans left Earth when astronauts reached orbit. We say a spacecraft left Earth when it escaped our planet's gravity. We say a probe left the solar system when it drifted beyond the sun's outer influence. And then, with the same easy verb, we ask whether humanity might someday leave the Milky Way. But those are not the same act. Not even close. They belong to entirely different scales of reality. And if we do not separate them carefully, the whole question starts to blur. Leaving Earth can sound like the early version of leaving the galaxy, as if one naturally leads to the other. As if they are milestones on the same road. But they are not simply steps of the same size. They are more like different worlds of difficulty, stacked one inside another, each much larger than the last. A person can leave a room, a ship can leave a harbor, a species may leave a planet, but leaving a galaxy is something else. It is not just farther. It is so much farther that using the same word for all of them almost becomes misleading. So before going any further, it helps to slow down and ask a quieter question. What, exactly, does it mean to leave home? And how many homes do we actually have? Because Earth is one kind of home. The solar system is another. And the Milky Way is another still. Each one holds us in a different way. Each one keeps us close for different reasons. And escaping one does not mean escaping the next. The smallest of these homes, though still enormous by human standards, is Earth itself. Earth holds us with gravity, with air, with warmth, with water, with all the conditions that made our existence possible in the first place. It is easy to forget how complete that support really is. A person can walk outside without carrying oxygen because Earth provides it. A child can drink from a glass of water because Earth keeps liquid water stable on the surface. Trees grow, clouds form, birds cross the sky, oceans move with the pull of the moon. So much of what we call ordinary life is really an invisible partnership with the planet. To leave Earth is not simply to go upward. It is to step outside a complete life support system that formed us down to the level of our bones, our blood, and our instincts. That alone is extraordinary. And yet humanity has already done it, at least briefly. When the first astronauts rose into orbit, they did something no previous creature on Earth had ever done. They passed beyond the atmosphere that had shaped every life before them. They entered a region where breathing was impossible without machines, where temperature could swing violently, where a thin wall of metal and a carefully controlled cabin stood between life and silence. That was leaving Earth in one sense, but not in the deepest sense. Because orbit is not freedom from Earth. Orbit is still a kind of relationship with Earth. In fact, it is an intimate one. A spacecraft in orbit is still firmly held by our planet's gravity. It is not hovering above Earth in independence. It is falling around Earth, always missing the ground because of its sideways motion. The astronauts aboard the International Space Station may seem far away, but in cosmic terms they're still almost touching home. They circle the planet in a continuous loop, seeing sunrise and sunset over and over, never truly departing the world below. Even the moon, distant and lonely as it appears in the night sky, is still part of Earth's immediate family. The Apollo missions were astonishing acts of courage and engineering, but they were not departures into the deep unknown of interstellar space. They were journeys within the local architecture of one planet and its companion. Remarkable, yes. Historic, absolutely. But still close, cosmically speaking. The moon is about 384,000 kilometers away. Light crosses that gap in a little over a second. By the standards of the galaxy, that distance is almost tenderly small. So the first thing to understand is this. Leaving Earth is real, but it does not mean leaving everything that feels like Earth's world. It means stepping outside the atmosphere. It means escaping the immediate pull of the planet. It does not mean you have escaped the larger nest that surrounds it. That larger nest is the solar system. And the solar system is so much bigger than most people naturally feel. Earth circles the Sun at a distance of about 150 million kilometers. That already sounds enormous, and it is. But Jupiter is much farther out. Saturn farther still. Uranus and Neptune lie at distances that stretch the imagination into something almost dreamlike. Sunlight, which reaches Earth in about 8 minutes, takes more than 4 hours to reach Neptune. And even Neptune is not really the edge. Beyond the major planets lies a colder, stranger region filled with icy bodies, dwarf planets, and scattered debris left over from the solar system's formation. Pluto lives there, in that dim frontier. Farther still is the Kuiper belt, then the even more distant Oort cloud, a vast sphere of icy objects so remote that it is less like a border and more like a fading whisper of the sun's influence. Already, the language begins to become uncertain. Where exactly does the solar system end? That depends on what you mean by end. If you mean the region dominated by the sun's planets, then the answer lies somewhere past Neptune and Pluto. If you mean the region where the solar wind pushes outward and creates a bubble in interstellar space, then you are talking about the heliosphere, which stretches much farther. If you mean the outer limit of the sun's gravitational reach, then the answer may extend outward for perhaps a light year or more, blending gradually into the gravitational environment of nearby stars. This matters because it shows that leaving the solar system is not a single event like crossing a city gate. It is more like moving farther and farther from shore, until the old coastline becomes too faint to matter in the same way. Voyager 1 is often said to have left the solar system, and in one important sense that is true. It crossed the heliopause, the boundary where the solar wind weakens and interstellar space begins to dominate. That was an extraordinary milestone. It meant that a machine built by humans had entered the medium between the stars. It was, in a quiet and beautiful way, the first touch of our species beyond the sun's immediate bubble. But even there, the journey is still astonishingly young. Voyager 1 has not left the sun's gravitational influence in the fullest sense. It has not escaped into some separate star system. It has not traveled anywhere near 1 light year from home. It is still, in many ways, a local artifact of our own star's neighborhood, drifting outward with patient dignity. So leaving Earth is one thing. Leaving the solar system is another. And the difference between the two is not just a matter of more fuel. It is a shift in scale so severe that ordinary intuition starts to fail. Imagine this in a softer way. Leaving Earth is like stepping out of your house. Leaving the solar system is like leaving not just your house, but your entire city, your whole region, perhaps even the continent that gave your language its shape. And then there is leaving the Milky Way. That is not leaving the city. That is leaving the world. Because the Milky Way is not merely the place where the solar system happens to be. It is the entire stellar civilization of our existence. Every star you see with your eyes at night belongs to this galaxy. The glowing band across a truly dark sky is not some distant object hanging above us. It is the inner light of the great structure we are already inside. A flattened spiral city of stars, dust, gas, black holes, ancient clusters, dead suns, forming worlds, broken worlds, quiet worlds, and perhaps living worlds. To say we live in the Milky Way is like saying a fish lives in the sea. It is not an address. It is an environment. And the solar system is only one tiny current within it. This is where many people, without realizing it, compress the levels together. We have some mental picture of space as mostly emptiness, with islands of stars scattered throughout. So once we imagine leaving our solar system, we unconsciously feel as if we have already entered the wider cosmic ocean in a meaningful way. As if the galaxy itself is just a loose background behind our local system. But that is not how it works. The stars around us are part of the Milky Way's body. They are not outside it. They are its neighborhoods. Leaving the solar system would not mean leaving the galaxy in the way sailing out of a harbor means leaving land behind. It would mean entering the streets of a city that is much larger than we had emotionally understood. And those streets are very far apart. The nearest star system, Proxima Centauri, is more than 4 light-years away. So even after leaving the solar system, even after escaping the sun's domain, a traveler would not find themselves in a busy crossroads of nearby suns. They would enter a darkness that remains mostly empty for years of light travel in every direction. The solar system would fall behind, yes. But the galaxy would still be there, immense and almost indifferent, surrounding the traveler on every side. This is why interstellar travel and intergalactic travel are not close cousins. Interstellar travel means moving between stars inside the Milky Way. Intergalactic travel means leaving the entire structure that contains those stars. One is already almost unimaginably difficult. The other stands another order of vastness beyond it. It may help to picture the Milky Way as a great luminous disk, roughly 100,000 light-years across and perhaps about 1,000 light-years thick in its main stellar disk, though its halo and gravitational reach extend far beyond. Our solar system lives somewhere in the outer suburbs of that disk, not at the center, not at the edge, but off to one side in a spiral arm region. From where we are, leaving the galaxy in the shortest geometrical sense might mean traveling upward or downward out of the disk rather than trying to cross its full width. That sounds encouraging for a moment. Until the numbers return. Even escaping vertically could require hundreds of light years, depending on how one defines truly outside the main populated disk. And hundreds of light years are still so far beyond present human travel capability that the phrase shortest route begins to sound almost ironic. Because the shortest route out of the Milky Way is still, for us, functionally endless. That is the real lesson hidden inside these nested homes. Earth feels large until you compare it to the solar system. The solar system feels vast until you compare it to the galaxy. And the galaxy feels almost complete, almost like the whole universe, until you look toward Andromeda and realize the darkness between galaxies is wider still. But at each layer, there is a psychological temptation to assume that leaving the current layer means we are nearly free, nearly out, nearly beyond. And that temptation is almost always wrong. Every time we reach the next threshold, we discover that the larger structure was waiting all along. This pattern is strangely human. In ordinary life, people often imagine that one move will change everything. A new city, a new job, a new decade of life, a new house, a new horizon. And sometimes things do change, beautifully and deeply. But often the new place reveals a larger structure you had not noticed before, something that was shaping you from the outside while you were focused on the smaller room. Space is like that, only more honest. Leave Earth, and the solar system appears. Leave the solar system, and the galaxy appears. Imagine leaving the galaxy, and the local group of galaxies appears, with Andromeda, Triangulum, dwarf galaxies, dark matter, and the patient gravity that binds them together. Home keeps expanding faster than the dream of escape. There is also something emotionally important here. When people say they want humanity to leave Earth, they usually mean survival. They mean becoming a multi-planet species so that one disaster cannot erase us. When they imagine leaving the solar system, they often mean expansion, curiosity, perhaps the beginning of a civilization that does not depend on one star alone. But leaving the Milky Way is different. It no longer feels like a practical survival move. It begins to feel symbolic, philosophical, almost mythic. Because there is no immediate need to leave the Milky Way. The galaxy is already so huge, and so rich in stars and planets, that humanity could spend ages beyond comprehension simply trying to understand a tiny fraction of it. If we ever became a true interstellar civilization, we would still have more than enough room, more than enough mystery, and more than enough potential futures here at home. So when we ask whether humans will ever leave the Milky Way, we are asking a question beyond necessity. We are asking whether the human impulse to cross the next boundary has any natural ending. And maybe it does not. Maybe curiosity has no edge. Maybe every home eventually produces a few minds that look past its walls, no matter how large the home is. That is a beautiful thought. But beauty is not the same as feasibility. And feasibility, for now, remains anchored to these nested scales. To leave Earth, we need powerful rockets, life support, shielding, and the ability to survive outside the atmosphere. To leave the solar system, we need machines or vessels that can endure immense durations, extreme cold, weak sunlight, and the long fade of communication across expanding distance. To leave the galaxy, we would need something else entirely. Not simply stronger propulsion, but a redefinition of what human travel can be. Longer-lived systems, more radical energy sources, entirely new forms of survival, navigation, and perhaps even identity. Because by the time a mission operates on galactic timescales, it begins to challenge the meaning of human presence itself. Who counts as the traveler? The person who launched? The descendants born aboard the vessel? The uploaded mind, if such a thing ever became possible? The machine carrying memories? The genetic line? The culture? The answer becomes less obvious the farther outward the journey goes. And this is why the three thresholds matter so much. They are not simply distances. They are transformations in what travel demands of us. Leaving Earth asks whether we can survive outside our planet. Leaving the solar system asks whether we can survive beyond our star. Leaving the Milky Way asks whether something recognizably human can survive across durations and distances so extreme that home itself may become memory rather than place. That is not just an engineering question. It is a civilizational question. Almost a spiritual one, if that word is used gently. And perhaps that is why this subject feels so restful and so haunting at the same time. It reminds us that our lives take place inside layers of belonging we rarely notice during ordinary days. We wake up, answer messages, make coffee, cross streets, go to work, return home, look at a screen, maybe glance at the moon for a moment without really letting it in. All the while, Earth is carrying us. The sun is holding Earth. The galaxy is holding the sun, and we live inside those enormous structures as casually as if they were nothing at all. Then one quiet question opens the whole thing again. What would it really mean to leave? Not to visit orbit, not to touch the moon, not to send a probe beyond the heliopause, but to truly leave. The more honestly we ask that, the more the answer changes from a destination into a ladder of impossible tenderness. First the planet, then the star, then the galaxy, each one a cradle, each one harder to outgrow than the last. And yet human beings have always looked toward edges. Not because edges are easy, but because once an edge is seen, it becomes part of the imagination. If you are enjoying the calm of this journey so far, you can gently leave a like, subscribe, or share where you're listening from tonight. It is always comforting to picture different people, in different quiet rooms around the world, thinking about the same sky. For now, let this settle in slowly. Leaving Earth is not leaving the solar system. Leaving the solar system is not leaving the Milky Way. And leaving the Milky Way is not simply one more step after that. It is the crossing of an entirely different order of distance, difficulty, and meaning. So before we imagine great ships rising toward another galaxy, we have to pause and face a more immediate truth. Even traveling between stars inside our own galaxy may already be one of the greatest challenges a civilization like ours could ever attempt. And that raises the next question naturally. If the layers of home are this vast, and if simply crossing between nearby stars is already so daunting, then what exactly makes interstellar travel so difficult in the first place? Not in a poetic sense. In a practical one. What are the real barriers that stand between humanity and the stars, even before the edge of the Milky Way comes into view? That is where the story goes next. Part 5: Why interstellar travel is so difficult. Once you stop thinking about space as a backdrop and start thinking about it as a real place, the difficulty of interstellar travel begins to change shape. At first, it sounds simple enough. The stars are out there. We are here. Build a powerful enough ship, point it in the right direction, and go. That is how most journeys have worked throughout human history. There is a destination, there is a vehicle, and there is enough determination to bridge the gap between the two. It feels like the kind of problem a patient civilization should eventually solve. But interstellar travel is not just a larger version of a sea voyage, or an air voyage, or even a voyage to the moon. It belongs to a different category. The difference is not only that the distances are bigger. It is that every part of the journey becomes hostile at the same time. The fuel problem grows. The time problem grows. The life support problem grows. The communication problem grows. The repair problem grows. Even tiny particles of dust become more dangerous. Even the emptiness becomes a challenge in ways that sound almost paradoxical. The difficulty is layered. And that is what makes it so important to understand calmly, step by step. Because when people imagine humanity traveling between the stars, they often imagine the destination first. Another sun, another planet, another horizon. But the true obstacle is not the destination. It is the space in between. That long, silent interval between one star and the next is where the dream becomes difficult. Not because it is dramatic in the way films often portray, but because it is indifferent. Space does not rush at you with monsters. It does not argue. It does not warn. It simply stretches onward for years, decades, centuries, or longer, and asks whether your ship, your systems, your supplies, and perhaps your entire civilization can remain intact for the whole crossing. That is a very different kind of challenge. The first barrier is still the one that quietly rules everything else. Time. Even if we stop talking about leaving the Milky Way and become much more modest, even if the dream is only to reach the nearest star system, the timeline immediately becomes difficult. Proxima Centauri is more than 4 light-years away. That sounds almost manageable after talking about galaxies, but only because the mind has already been softened by much larger numbers. In truth, 4 light-years is enormous. It is a distance that makes nearly all current spacecraft speeds feel irrelevant. At the speeds of our fastest outward probes, the trip would take tens of thousands of years. That is not a mission. That is not even a civilization's usual planning horizon. That is a duration long enough for languages to change beyond recognition, for coastlines to shift, for entire cultural identities to appear and disappear. A journey that long would no longer feel like transportation. It would feel like a separate branch of history breaking away into the dark. So the first reason interstellar travel is difficult is painfully simple. Even the nearest stars are too far away for slow ships to matter. And that creates pressure on everything else. Because if you cannot shorten the trip, then the travelers must survive longer. Their food must last longer. Their machines must function longer. Their habitat must remain stable longer. Their purpose must remain meaningful longer. The burden spreads outward into every system on board. That is why the second barrier is energy. To go faster, you need more energy. Much more. And here the universe is quietly brutal. Speed is expensive. Not in the ordinary human sense of expensive, where a larger budget solves the issue, but in the physical sense. Every increase in velocity requires more energy, and the faster you try to go, the more severe the cost becomes. A ship that wants to cross interstellar distances in decades rather than millennia needs to move at a significant fraction of the speed of light. That is not a small upgrade from current spacecraft. That is an entirely different category of motion. And to reach that category, a ship needs a source of propulsion far beyond what chemical rockets can reasonably provide. Chemical rockets are magnificent for leaving Earth. They are one of the great inventions in human history. But they are deeply unsuited for long interstellar journeys. They burn through fuel quickly, they carry enormous mass, and the energy density of chemical fuel is simply too low for the distances involved. You can use a chemical rocket to break free of a planet. You cannot use one, at least not realistically, to make the stars feel close. So interstellar travel quickly pushes us beyond ordinary rockets and into much stranger territory. Nuclear propulsion, fusion concepts, light sails, antimatter in theory. Concepts that sound futuristic not because they are glamorous, but because only something much more powerful than our present systems has even a chance of mattering. But this introduces another old problem in a harsher form. The more fuel you need, the heavier the ship becomes. The heavier the ship becomes, the more energy you need to accelerate it. And the more energy you need, the more fuel you have to carry. This is the tyranny hidden inside rocketry. It is not enough to have a powerful engine. The engine must also push its own fuel, and the fuel for later, and the structure holding everything together, and the shielding, and the supplies, and perhaps an entire rotating habitat if humans are on board. Every solution adds weight. Every answer becomes part of the next problem. This is why some of the most serious ideas for interstellar travel do not try to carry all their energy the way a normal rocket does. They try to borrow it from outside. A light sail, for example, would use intense beams of light or lasers to push a lightweight craft forward, allowing the energy source to remain behind rather than traveling with the ship. It is an elegant idea, and a useful reminder that even our engineering imagination begins to change when distance becomes cosmic. We stop thinking like drivers carrying gasoline and start thinking like beings trying to surf the architecture of physics itself. Still, propulsion is only the first difficulty. Even if a ship could be accelerated to extraordinary speed, the journey would remain dangerous. Because space is not empty in the comforting way people imagine. It is empty in the treacherous way deserts are empty. There may be long stretches of nothing useful, but that does not mean there is nothing there. Between the stars, there is thin gas, stray atoms, radiation, magnetic fields, dust grains, and the leftover debris of ancient processes. At everyday human speeds, small particles are not especially threatening, but at interstellar speeds, they become serious hazards. A grain of dust striking a ship at a meaningful fraction of the speed of light carries enormous energy. It is no longer a soft speck drifting in the dark. It becomes an impact event. That means a fast interstellar vessel would need shielding, probably a great deal of it. And shielding means mass. And mass means more propulsion burden. The problems keep feeding one another. There is something almost elegant about the cruelty of this. If you want to go faster, you need more energy. If you go faster, tiny particles become more dangerous. To survive those particles, you need more shielding. More shielding means more mass. More mass means more energy again. The universe does not say no directly. It simply raises the price at every step. Radiation is another barrier, and a quieter one. On Earth, we live beneath the protection of a thick atmosphere and a magnetic field. They are so constant that most people rarely think about them, but they are guardians all the same. They shield us from a large fraction of the harmful radiation flowing through space. Outside that shelter, things change. The sun produces radiation. Deep space contains cosmic rays, which are high-energy particles moving through the galaxy at enormous speed. Over short missions, these exposures are already a concern. Over long missions, they become a defining challenge. For robotic probes, radiation is an engineering problem. Electronics must be hardened. Systems must tolerate failure. But for human beings, radiation is biological. It damages cells. It increases cancer risk. It threatens the nervous system. It accumulates over time. A short trip is one thing. A multi-year journey is another. A generational journey is something else entirely. This is part of what makes interstellar travel more difficult than simply going farther. The environment is not only distant, it is corrosive to living systems. And unlike a mountain climber or a sailor, a crew in deep space cannot easily retreat to a safer place. There is no nearby harbor. There is no coast guard. There is no weather report that can redirect you to a warm port where repairs can be made. Once you are truly between stars, your ship is not just transportation. It is the entire world. That leads to another major obstacle, one that may sound mundane compared to fusion engines and relativistic physics, but is no less important. Maintenance. Machines fail. They fail on Earth, where help is close. They fail in cities with spare parts and trained technicians and bright rooms full of tools. They fail in aircraft. They fail in submarines. They fail in data centers. They fail in hospitals. They fail in orbit. Now imagine a machine that must not merely operate for a few years, but for decades, or centuries, or perhaps much longer. A vessel with life support, guidance systems, structural materials, shielding, thermal regulation, recycling systems, computing hardware, communications equipment, and possibly artificial gravity systems if the mission is carrying human beings for the long term. What does it mean to repair such a ship halfway to another star? What factory supplies the replacement parts? What technician trains for every failure mode of every system over generations? What happens if the problem is not one thing breaking, but a slow drift of many systems away from their design tolerances over time? This is one of the least cinematic barriers in all of space travel, and one of the most serious. A long mission does not only require a strong launch, it requires a self-sustaining ecosystem of reliability. That includes software. It includes materials aging in unexpected ways. It includes seals drying out, circuits degrading, sensors drifting, microscopic fractures growing, lubricants behaving differently over long time spans, and machines interacting with one another in ways no simulation fully predicted. A starship, if humans ever build one, may need to function less like a vehicle and more like a small civilization that can manufacture, diagnose, recycle, and adapt indefinitely. And that thought alone reveals how far interstellar travel is from ordinary transport. Then there is communication. On Earth, communication is immediate enough that we often take it for granted. A person sends a message. Another reads it. Instructions change. Questions are answered. Guidance can arrive in minutes or seconds. Even missions to Mars, difficult as they are, still operate within a system where communication delays are measured in minutes, not years. Between stars, communication changes character. At Proxima Centauri, a message traveling at light speed would still take more than 4 years to arrive. A reply would take more than 4 years to come back. A simple question and answer could require nearly a decade. There would be no real-time control, no meaningful live support, no quick correction from Earth. The farther a mission traveled, the more it would become psychologically and operationally independent. This matters because it changes how a mission must be designed. The ship cannot depend on home in the ordinary sense. It must be able to make decisions, handle emergencies, and preserve coherence on its own. It must carry not just hardware, but autonomy. That is difficult enough for robotic missions. For human missions, it becomes deeper. Because human beings do not merely need oxygen and calories. They need context. They need trust. They need purpose that can survive silence. A crew hearing from Earth only after years of delay would inhabit a different emotional universe than any humans before them. Their home would still exist, but always in the past. Every message arriving from Earth would be old news by definition. Every message sent outward would be an artifact launched into time. This may sound poetic, but it is really practical. Psychology is part of mission design. Isolation can destabilize judgment. Confinement can reshape social bonds. Repetition can wear down meaning. Even on Earth, humans in remote stations, submarines, or polar outposts experience stress, conflict, monotony, and emotional strain. Those settings are difficult despite the fact that return is possible and rescue, at least in principle, exists. Deep interstellar travel removes those comforts. And that is before we even discuss the body itself. The human body evolved under one gravity, one atmosphere, one day-night cycle, one biosphere, and one very specific chemical history. Space does not naturally support any of these. In orbit, astronauts lose bone density and muscle mass without constant exercise. Fluids shift. Sleep changes. Immune function can change. Eyesight can be affected. These are already meaningful issues on missions that last months. What happens over decades? What happens to children born in artificial environments, if such missions ever became generational? What happens to development, reproduction, disease, aging, and adaptation in habitats detached from Earth for extreme spans of time? Some of those questions belong more fully to another part of this journey, because they concern the survival of humans in a direct sense. But even here, they remind us of something important. Interstellar travel is difficult not only because of the ship, but because of the passenger. A robotic probe can arrive broken and still succeed if its instruments work. A human mission must preserve a living world. Then there is navigation, which sounds simple only until the scale is faced honestly. When a destination is very far away, tiny errors become enormous over time. A slight drift in direction, a minor miscalculation, a subtle perturbation, an unexpected interaction with dust, gas, or magnetic environments, all of it can matter. A ship traveling for decades or longer cannot simply point itself once and trust the rest to fate. It must measure, correct, adapt, and preserve accuracy across a journey longer than most human institutions remain stable. And if the mission is fast enough for relativistic effects to matter, then navigation becomes even more delicate. Time, reference frames, and observed positions do not behave with comforting simplicity at those speeds. The stars themselves are moving. The destination is not frozen in place waiting politely. The galaxy is dynamic. Everything is in motion. So even the act of aiming becomes a science of patience. There is also a more philosophical difficulty hiding underneath all the others. Interstellar travel asks a civilization to commit to results it may never personally see. That is unusual for human societies. People can plant trees whose shade they will never sit beneath, yes. They can build cathedrals they will never see completed. They can begin scientific projects whose final fruits belong to future generations. Human beings are capable of that kind of long thinking at our best. But interstellar travel may demand it on a scale beyond anything we have yet proven politically, culturally, or economically. Who funds a mission whose arrival lies centuries away? Who maintains commitment when the original planners are gone, the original nations perhaps altered, the original motivations forgotten or transformed? What kind of civilization sustains intention across that span? This is not a technical weakness. It is part of reality. A star mission is not just a machine problem. It is a continuity problem. Can a species remain coherent long enough to send itself into the dark? And if it cannot, then even a physically possible journey may remain socially impossible. That may be one of the quietest truths in this whole discussion. Sometimes the barrier is not the universe alone. Sometimes it is the difficulty of remaining ourselves over long durations. Still, none of this means interstellar travel is meaningless to imagine. Quite the opposite. To look honestly at these barriers is to understand the scale of the challenge, and also the scale of what human intelligence has already begun. Even now, with all our limitations, we have sent machines beyond the planets. We have crossed into interstellar space with instruments. We have learned to build probes that survive in darkness for decades. We have imagined propulsion systems that do not yet exist but are grounded, at least in part, in real physics. We have learned to think in terms of light years at all, which is itself a kind of mental evolution. That matters. Because one of the most human things about us is not that we immediately conquer every distance we see. It is that we learn to see the distance clearly in the first place. And perhaps that is why this subject feels so restful at night. It puts ordinary worries into a larger frame. Not by dismissing them, but by reminding us that we live inside a universe where the spaces between things are vast beyond instinct, where even reaching the nearest star may demand more from a civilization than anything in its prior history. There is humility in that, and there is also comfort. Because if the stars are hard to reach, then home becomes more meaningful too. Earth is not merely where we happen to be. It is the one place we know can grow forests, oceans, weather, memory, language, children, music, grief, laughter, and all the fragile things that make a human life feel human. The difficulty of interstellar travel does not cheapen the dream of the stars. It deepens the value of the shore we stand on while dreaming. If this calm walk through the problem is helping you settle in, you can quietly leave a like, subscribe, or share where you're listening from tonight. I always enjoy seeing the different corners of Earth from which people are looking up and wondering the same things. For now, let one quiet conclusion rest here. Interstellar travel is difficult because every challenge arrives together. Distance, energy, time, radiation, impact risk, maintenance, communication, isolation, biology, navigation, and civilizational patience all converge in the same narrow corridor between stars. It is not one locked door. It is a hallway of them. And yet humans keep imagining a way through. So the next question becomes not whether the problem is hard. That part is already clear. The deeper question is whether future engines, future physics, or future forms of travel might change the scale of what is possible. Could new propulsion systems make the stars less distant than they seem now? Could some future civilization learn to cross the dark more gracefully than we can imagine from our small corner of time? That is where the story turns next. Part 6. Could future engines change everything? After looking honestly at all the barriers between us and the stars, it is tempting to fall into one of two moods. The first is resignation. The distances are too great, the ship would be too fragile, the human body too vulnerable, the mission too long, the energy too expensive. In that mood, the story seems finished before it has really begun. The second mood is the opposite. Somewhere in the future, we tell ourselves, someone will invent a miracle engine, a perfect machine, A breakthrough so complete that all the old problems will shrink at once. The stars will stop feeling far. The galaxy will stop feeling closed. Human beings will rise from Earth the way birds rise from a field, and the old limits will become just another phase we outgrew. Both moods are understandable. And both, in their own way, are too simple. Because the truth is quieter than either of them. Future engines might change a great deal. They may change more than we can comfortably imagine from our present moment. They may shorten journeys that now seem absurd. They may allow robotic probes to cross interstellar distances in lifetimes instead of eras. They may even, one day, carry living crews farther than anything we now regard as practical. But no engine, however advanced, gets to negotiate with the basic structure of reality. That is the part worth sitting with. A better engine does not erase distance. It only changes your relationship to it. A faster ship does not remove danger. It rearranges the dangers. A more powerful civilization does not make the universe small. It only makes a slightly larger portion of it accessible. And yet that is still a very meaningful thing. Because sometimes the future does not arrive as magic. Sometimes it arrives as a series of partial victories that, taken together, begin to feel almost miraculous. So now the question becomes less romantic and more interesting. Could future propulsion systems make a real difference? Could they change the story enough that leaving the solar system stops being fantasy, that reaching nearby stars becomes something more than a thought experiment, and that the edge of the Milky Way, while still painfully far, moves from impossible to merely extreme? To answer that, it helps to begin with a very human habit. Whenever a frontier resists us, we imagine a tool that will tame it. When the sea resisted us, we built stronger ships. When mountains resisted us, we cut roads and tunnels. When gravity resisted us, we built rockets. So naturally, when interstellar distance resists us, we imagine engines. Not because engines solve everything, but because movement has always depended on them. A frontier without propulsion is just scenery. A frontier with propulsion becomes a challenge. And for all of human history, propulsion has steadily improved. Walking became riding. Riding became sailing. Sailing became steam. Steam became internal combustion. Combustion became flight. Flight became rocketry. Each stage would have seemed implausible to someone standing far enough back in time. So it is not foolish to believe that propulsion will continue to advance. In fact, it would be strange to assume it has already reached its final form. But space is not a road, and it is not an ocean. That is why the next leap in propulsion matters so much more than the earlier ones did. On Earth, many journeys became easier because the environment itself helped us. Roads could be built. Air could support wings. Water could carry hulls. Refueling stations could be placed along the way. Repairs could happen in towns and ports and cities. Deep space offers almost none of that generosity. It is cold, sparse, and unforgiving. If you want speed there, you usually have to bring the means with you, or invent some way of borrowing energy from elsewhere. That is why the engines of the future tend to fall into two broad dreams. The first dream is to carry far more powerful energy sources than we have now. The second dream is to stop carrying so much of the energy at all. The first path leads to ideas like nuclear propulsion, fusion propulsion, and, in more speculative territory, antimatter propulsion. The second path leads to ideas like light sails and beam-driven craft, where much of the push comes from outside the ship rather than from fuel carried on board. Each of these ideas is fascinating. Each is rooted, at least in part, in real physics. And each comes with its own quiet price. Let us begin with nuclear propulsion, because in many ways it is the least exotic of the future options, and perhaps the most important bridge between what we can imagine now and what may come later. Chemical rockets work by rearranging the energy stored in chemical bonds. Useful, dramatic, and necessary for launching from Earth, yes, but limited. Nuclear reactions, by contrast, release far more energy from much smaller amounts of mass. That difference alone makes them deeply attractive for long-range space travel. One version is nuclear thermal propulsion. In simple terms, a reactor heats a propellant, often hydrogen, and expels it at very high speed, producing thrust more efficiently than a chemical rocket can. Another version is nuclear electric propulsion, where a reactor generates electricity that powers highly efficient engines over long periods. These systems are not fantasy. Variants of them have been studied seriously for decades. They do not grant starflight overnight, but they could make travel within the solar system faster and more flexible. Mars missions could shorten. Heavy cargo could move more effectively. Outer planet exploration could become more practical. That may sound modest compared with the dream of leaving the Milky Way, but it matters more than it seems. Because the road to the stars, if it ever opens at all, may begin with becoming truly comfortable in our own solar system. A civilization that cannot move efficiently between planets is not yet a civilization ready for interstellar ambition. It is still learning how to breathe beyond its cradle. So nuclear propulsion may not be the engine that carries humans to another galaxy, but it may be one of the engines that teaches us how to live and move at larger scales than we do now. Then comes fusion, and with fusion the tone changes. Fusion is the process that powers the stars themselves. It is what makes the sun shine. It joins light atomic nuclei together and releases tremendous energy in the process. For decades, fusion has lived in the human imagination as a kind of disciplined miracle. Not magic, because the physics is real, but miracle enough that its practical mastery always seems to belong to the next chapter. If humanity ever learns to use fusion reliably and compactly for propulsion, the implications could be profound. A fusion-powered spacecraft might accelerate for long periods with far greater efficiency than chemical systems allow. Speeds once treated as absurd could begin to enter serious conversation. Not half the speed of light, perhaps, and not without immense engineering burdens, but enough to make some interstellar probes conceivable on timescales shorter than civilizations. That is the important distinction. Fusion does not necessarily make the stars near, but it may make them reachable by entities that still remember why they started. And that alone would transform the emotional geography of the cosmos. A star system 4 light-years away still feels almost eternal if the journey takes tens of thousands of years. It feels different if a probe can arrive in a few decades, or a century, or some other span that remains meaningfully connected to the originating civilization. The gap is still enormous. But it stops feeling like a separation between worlds and starts feeling, perhaps, like a very long voyage. There is something deeply human about that shift. Not because it makes the universe small, but because it makes ambition feel proportionate again. Still, fusion is not a free gift. A fusion engine must confine and control processes that are notoriously difficult to sustain even in experimental conditions on Earth. Then it must do so inside a spacecraft. Then it must remain reliable over long durations. Then it must survive vibration, radiation, failures, thermal stress, and all the other indignities of engineering. Then, if humans are on board, it must do all this without becoming its own source of danger. So fusion is promising, yes. But it is promising in the sober way mountains are climbable. It may be possible. It may even someday be practical. But the slope remains steep. Then, farther out in the landscape of ideas, there is antimatter. Few concepts in space propulsion sound more dramatic. Matter and antimatter annihilate each other on contact, releasing enormous energy. In pure energy density terms, antimatter is astonishing. So naturally it appears in many conversations about future starships. If you want the most powerful conceivable fuel, antimatter enters the room very quickly. But here we move into a quieter kind of difficulty. It is one thing to say that antimatter contains immense energy. It is another to produce it in meaningful quantities, store it safely, control it precisely, and use it in a propulsion system without turning the ship into a very expensive catastrophe. At present, antimatter exists more as a signpost of what physics allows than as a realistic near-future engineering path. It reminds us that the laws of nature do not forbid extreme energy density. But it does not tell us that a civilization like ours can harness it at useful scale. That difference matters. Because when people hear about advanced propulsion, they often confuse the physically imaginable with the civilizationally achievable. The universe contains many possibilities. That does not mean all possibilities are waiting politely for us to build them. And that brings us to a different family of ideas entirely, one that may prove more practical in the nearer term than carrying gigantic stores of onboard fuel. The idea is beautifully simple. What if the ship does not carry the push? What if the push comes from home? This is the dream behind light sails and beam-driven propulsion. A sail in space can be pushed by light, not strongly by ordinary sunlight alone, at least not enough for large human vessels, but in principle by powerful directed beams, such as lasers. If a lightweight probe carried a reflective sail, and a powerful beam system remained behind in the solar system, that probe could be accelerated to very high speeds without dragging along all the fuel needed for the trip. This is one of the most elegant ideas in all of interstellar planning because it sidesteps a central trap: fuel mass. The craft can remain small and light, while the energy infrastructure stays at home. And if this works, even on a modest scale, it may be one of the first real ways humanity reaches beyond the solar system in meaningful timeframes. Not with giant human starships. Not at first. But with very small robotic probes. That may sound disappointing until you think about what it would actually mean. A tiny robotic craft sent toward another star at a significant fraction of light speed. An object built by human hands crossing the dark between suns not over millennia, but perhaps over decades. A message in machine form moving into another system while the civilization that launched it is still alive to wait for news. That would not be intergalactic escape, but it would be a revolution in our relationship to the stars. And revolutions do not always begin at the largest scale. Sometimes they begin with something small enough to prove that the frontier is real. Of course, beam-driven sails also have their costs. The infrastructure required could be enormous. The aiming must be precise beyond ordinary intuition. The probe, once accelerated, may have limited ability to slow down at the destination unless another system is waiting there, which it will not be. So many such missions might become flybys rather than arrivals. Brilliant flashes of contact rather than settlement. Still, even that matters. Because history suggests that exploration often begins with glimpses before it deepens into presence. There are also stranger ideas that live near the edge of accepted speculation. Concepts like interstellar ramjets, which would collect sparse hydrogen from space itself. Exotic propulsion ideas that depend on physics not yet usable or perhaps not even truly available in the way people hope. And, hovering beyond all of them, the old fantasy of warp drives or wormholes, the dream that spacetime itself might someday be bent into shortcuts. These ideas are captivating, and there is no harm in letting the imagination rest on them for a moment. But the calm answer is that none of them currently offers humanity a dependable road outward. Some may remain mathematical curiosities. Some may collapse under closer scrutiny. Some may teach us useful things even if they never become machines. And some, perhaps, may surprise future generations. But if we are being honest, the most grounded hope for future propulsion lies not in magical shortcuts, but in better mastery of energy, better engineering, and better patience. That may sound less glamorous. It is also more believable. Because the future does not have to hand us a miracle in order to change everything that matters. Imagine, for a moment, a civilization 2 or 3 centuries ahead. Not omnipotent. Not fictional. just more mature in space than we are. Perhaps it has reliable nuclear systems, partial fusion capability, deep industrial infrastructure in the solar system, large orbital construction, better closed-loop life support, autonomous repair systems, and a long cultural memory of living beyond Earth. That civilization would still face all the same universal barriers we do. And yet its relationship to those barriers would be different. Mars would not seem remote. The outer planets would not feel unreachable. Long-duration missions would not seem unnatural. Gigantic energy projects in space might no longer sound absurd. And from within that world, the first real interstellar probes might emerge. Not because physics changed, but because civilization changed. That point is easy to miss, and maybe it is one of the most important in this entire discussion. Sometimes the decisive engine is not only a machine, it is a society capable of building and sustaining the machine. A powerful engine without a stable civilization behind it is only a burst. A stable civilization without powerful engines is only patience. The future may require both. Still, even if propulsion improves dramatically, the question hanging over all of this remains the same. Would it be enough to leave the Milky Way? And here, the answer becomes calm again. Probably not in the near sense people usually imagine. Better engines may open the solar system. Better engines may open nearby stars. Better engines may allow robotic emissaries to touch the first edge of true interstellar exploration. Over very long timescales, they may even support human journeys between star systems, especially if those journeys become generational or involve forms of suspended biology or machine partnership we do not yet possess. But leaving the Milky Way is another scale of ambition. Even with radical propulsion improvements, the galaxy remains vast. Hundreds of light years to rise out of the disk. Tens of thousands of years even at 1% of light speed. Millions of light years to Andromeda. The numbers do not disappear simply because our engines become nobler. So no, a future engine probably does not make the Milky Way suddenly easy to leave. But it could still change the meaning of the question. Because once a civilization can truly move between stars, even slowly, its home changes shape. The galaxy stops being a distant map and becomes a lived environment. The spiral arms become destinations. Nearby systems become provinces of a larger human story. Distances that once felt terminal begin to feel navigable, if still immense. And that may be enough to alter our sense of fate. Perhaps the deepest role of future engines is not to free us from the galaxy at all. Perhaps it is to teach us that the galaxy itself is already more than enough. Hundreds of billions of stars. More worlds than any species could exhaust. More history, more silence, more possible forms of life and failure and wonder than we will ever fully hold in mind. If better propulsion lets humanity spread carefully, slowly, thoughtfully through even a tiny fraction of that vast structure, then the old question of escape may start to feel less urgent. Not because it was answered, but because home grew larger. And yet, the dream of escape would probably remain. Human beings do not stop looking at the next horizon simply because the current one turns out to be spacious. The mind keeps reaching. It always has. Which is why this conversation, however technical it sometimes sounds, is not really only about machines. It is about hope under the laws of physics. How far can hope travel before it becomes something else? How much can a civilization change the practical meaning of distance without pretending distance no longer exists? Those are gentler questions than they first appear. They do not ask us to conquer the stars tonight. They only ask us to be honest about the difference between fantasy and possibility, and to leave room for the future to surprise us without demanding that it behave like a fairy tale. If this slow exploration is helping you unwind, you can quietly leave a like, subscribe, or share where you're listening from tonight. It is always grounding to imagine people in different rooms, different countries, all drifting under the same galaxy while thinking about the same distant lights. For now, let one thought rest softly in place. Future engines might change a great deal. They might shorten journeys, open the solar system, and carry our first true messages to the stars. They might make humanity less local than it is now. But even the most powerful engine cannot answer the final question alone. Because movement is only one part of the journey. The other part is the traveler. And even if a future civilization builds a ship fast enough to cross the dark, another problem waits quietly inside the cabin. Would human beings themselves survive a voyage like that? Not just technically, not just physically, but emotionally, biologically, and over the long duration such a journey would demand. That is where the story goes next. Part 7. Would humans even survive the journey? A powerful engine can move a ship, but it cannot, by itself, carry a human life safely through the dark. That is where this question becomes quieter, and in some ways more unsettling. Because once we stop asking how fast a vessel might travel, we begin asking something much more intimate. What would happen to the people inside it? Could a human being actually endure the journey between stars, not just for a few days or months, but for years, decades, or far longer? Could a family? Could a whole community? Could children be born on such a voyage and still remain, in any meaningful sense, travelers from Earth? These are not small questions. They are the kind that turn a machine into a mirror. Because the deeper we imagine interstellar travel, the more clearly we begin to see what a human life really depends on. Not just oxygen, not just food, not just temperature and radiation shielding. We depend on rhythms, gravity, other people, sunlight, or something like it, a horizon, a sense that the world around us is stable enough to trust, a sense that time is moving toward something we can understand. On Earth, all of that is so normal we almost never notice it. You wake up in a room that belongs to a planet. Morning arrives on schedule. Gravity holds you gently but constantly. Air is everywhere. Water comes from taps, rain, rivers, clouds, pipes, bottles, mist. Food grows from soil or swims in oceans or is carried across continents by systems so familiar that most of the time we do not stop to think how extraordinary any of it really is. Even the silence of a night room is still a silence held inside an atmosphere, under a sky, on a world full of life. A starship would have none of that by default. It would have to build an artificial version of almost everything we take for granted. And it would have to keep that artificial world stable for longer than any human-built life support system has ever had to function before. That alone should slow the mind down. Because when people imagine leaving the Milky Way, or even just reaching another star, the imagination often rushes straight to the launch. The ship rises. The engines burn. Earth fades behind the crew. There is courage, wonder, sacrifice, perhaps a little sadness. It is a powerful image. But launch is not the real test. The real test begins later. It begins when the ship has been traveling for months, then years, then decades. When the novelty has burned away. When the walls are still the same walls, the corridors the same corridors, the faces mostly the same faces. When Earth is too far away to rescue anyone, too far away to advise in real time, perhaps even too far away to feel emotionally immediate. That is when interstellar travel stops being a dramatic departure and becomes a condition of living. And that is where human survival becomes the true center of the question. The first challenge is the body itself. Human beings evolved under one gravity. Earth's gravity is not simply a number in a physics equation. It is a constant sculptor of our anatomy. It shapes our muscles, our bones, our balance, our circulation, even the way fluids distribute through the body. In orbit, astronauts already experience what happens when that sculptor is removed. Bone density declines. Muscles weaken. Fluids shift upward. Faces become puffier. Legs thin out. Eyes can change. The spine can lengthen slightly. Sleep can become strange. Even with exercise, the body begins adapting to a world that does not naturally support the form it was designed to keep. And those effects occur over months. What happens over years? What happens over decades? That is still, in many ways, an unanswered question. A long-duration human mission would almost certainly need some kind of artificial gravity, perhaps through rotation. A rotating habitat could use centrifugal force to create a sensation similar to gravity, allowing bodies to live in a more Earth-like condition. But even that introduces complexity. The structure must be large enough, or rotate carefully enough, to avoid severe discomfort. It must remain mechanically stable. It must keep functioning not just during a crossing of days or weeks, but through spans of time so long that ordinary engineering reliability begins to feel fragile. So even before we talk about emotion, or food, or isolation, the body has already started negotiating with the ship. And the body is not the only thing Earth has quietly trained. The mind has been trained too. Humans are not only biological creatures. We are environmental creatures. We are shaped by weather, changing seasons, open skies, different rooms, unexpected walks, voices from outside, the smell of rain, the sound of wind, the ordinary variety of a living planet. These things matter more than people often realize. A healthy mind does not live on information alone. It lives partly on change, on texture, on contact with a world larger than the self. A starship would be, by design, a closed world. Efficient, regulated, controlled, repetitive, the same surfaces, the same systems, the same limited set of possible movements. Perhaps simulated parks, perhaps projected skies, perhaps carefully designed communal spaces meant to reduce psychological strain. But no matter how sophisticated the architecture becomes, the truth remains. The ship is not Earth. It is a machine trying to imitate just enough of Earth to keep human beings coherent. That may be possible. But possible is not the same as easy. Imagine living your entire life in a place where every breath depends on machinery. Every liter of water must be reclaimed. Every bit of waste becomes part of a recycling loop. Every crop is measured, monitored, optimized. Every failure is not an inconvenience, but a threat. That kind of life might become normal to those born into it, but it would not be a casual normal. It would be a maintained normal, delicate beneath its routines. And that leads naturally to food. On Earth, food is not simply fuel. It is culture, memory, comfort, identity, ritual. A bowl of soup on a quiet night means more than calories. So does coffee in the morning. So does fruit in a market, bread from an oven, rice on a table, the smell of a kitchen at the end of the day. Food belongs to human life at more than one level. A starship would need food systems that are closed-loop, reliable, and long-lasting. Stored supplies can support short missions, but not journeys measured in generations. That means agriculture of some kind. Not romantic fields beneath open skies, but hydroponic systems, controlled environments, carefully managed nutrient cycles, artificial lighting, pest control, seed preservation, pollination strategies, microbial balance, waste conversion, redundancy. The more you think about it, the clearer it becomes. A long-range human vessel would not be a ship in the ordinary sense. It would be a small world. And worlds are hard to manage. Even ecosystems on Earth, large and self-repairing as they are, can become unstable. Crops fail. Diseases spread. Invasive species disrupt old balances. So imagine trying to preserve an artificial ecosystem inside a sealed vessel. Every organism must be chosen with care. Every biological interaction must be understood well enough to avoid collapse. Water must circulate. Air must be scrubbed and renewed. Soil, if any is used, becomes part of a designed biochemical system. Even tiny disruptions could matter enormously over time. This is one reason the dream of interstellar human travel often drifts, almost without noticing, from engineering into ecology. To keep humans alive far from Earth, you do not simply need fuel and walls. You need a functioning biosphere, or something close enough to one. And once you have something that complex, another problem emerges. Repair. Machines break, yes. But living systems drift. Plants mutate. Microbes evolve. Closed habitats develop quirks. Minor imbalances, if not noticed early, can accumulate slowly until they become serious. A healthy starship would need not just repair crews, but gardeners, doctors, biologists, engineers, teachers, cooks, psychologists, perhaps historians, perhaps artists. It would need people whose work is not simply technical, but civilizational. That word matters here. Because by the time a mission becomes long enough for human survival to dominate the problem, the ship stops behaving like transport and starts behaving like a society. And societies carry their own difficulties. People disagree. People form alliances. People fall in love. People resent one another. People become parents, or choose not to. People grieve. People get bored. People long for things they cannot have. People pass on values, habits, fears, beliefs. Children grow up shaped not only by the physical environment, but by the social world surrounding them. A long interstellar voyage would contain all of that. In fact, it might contain it in intensified form. Because on a starship, there is no countryside to escape to. No other city. No separate country. No easy privacy from the deeper fact of dependence. Everyone aboard would be part of the same closed system, materially and emotionally. A serious conflict would not simply be unpleasant. It could threaten the whole mission. A cultural drift away from maintenance discipline could become dangerous. A loss of trust in leadership, or in the purpose of the voyage itself, could reshape the destiny of everyone aboard. This is where the old fantasy of a heroic crew quietly gives way to something more realistic. A true multi-generational human mission would not mostly be about heroism. It would be about governance, education, meaning, conflict resolution, institutional memory. It would be about whether a community can remain healthy while cut off from every outside shore. That is not impossible in principle. Human beings are astonishingly adaptable. We have lived in deserts, islands, frozen regions, dense cities, forests, mountains. We have survived prisons, submarines, polar stations, wartime shelters, and lifeboats. We know how to build culture under constraint. But interstellar travel would take that adaptability and stretch it farther than anything in our history. There is also the question of generations. If a mission lasts long enough, the people who arrive will not be the people who departed. That changes the emotional meaning of the journey completely. The original crew might think of themselves as explorers or guardians of a plan. Their children might think of the ship as home. Their grandchildren might know Earth only as a story. Their descendants, centuries later, might not experience the voyage as a voyage at all. For them, the ship may simply be the world, and the destination a distant idea inherited from ancestors they never met. That raises a difficult and strangely tender question. Do future generations have an obligation to continue a mission they did not choose? It is easy to answer yes from the comfort of Earth, where the mission is abstract and noble. It may feel different for a teenager born inside a rotating habitat who has never seen an ocean, never felt real wind, never walked beneath an unsimulated sky, and has been told since childhood that their life belongs partly to a destination centuries away. Would that feel meaningful? Would it feel oppressive? Would it become normal? No one knows. And perhaps no one can know until such a society actually exists. This is why interstellar survival is not just about preventing death. It is about preserving a form of life that still feels worth living. That may be the deepest challenge of all. Because a ship can keep people breathing while still failing to keep them human in the fuller sense they hoped to preserve. Not biologically human, perhaps, but emotionally, culturally, existentially human. A mission that survives physically while collapsing into despair, violence, stagnation, or inherited bitterness might still count as a technical success on paper. But it would not be the kind of success most people mean when they imagine humanity reaching the stars. Then there is reproduction, one of the least discussed and most serious unknowns. Human reproduction has evolved under Earth conditions. Pregnancy, childbirth, infancy, development, childhood growth, all of it depends on biology interacting with gravity, environment, nutrition, stress, disease, and care structures in ways that are not fully separable from our planet. We do not yet know what healthy multi-generational reproduction would look like in long-term artificial habitats. We do not know how low gravity, radiation exposure, confinement, or closed genetic populations might affect outcomes over many generations. A serious starship would need to think about this from the beginning. How large must the population be to remain genetically healthy? How would medical care evolve across generations? How would childhood education shape people whose entire universe is built of corridors, gardens, recycled air, and old stories of Earth? Would they dream of arriving somewhere new? Or would they dream of escaping the mission itself? These questions may sound dramatic, but they are actually very practical. A voyage lasting many human generations is not merely transporting people through space. It is creating a branch of humanity under artificial conditions and asking that branch to remain stable enough to continue. That is a large request. There is another quiet issue too. Time. Not just mission time, but felt time. On Earth, life is marked by layers of change. The body ages. Neighborhoods shift. Seasons return. Technology changes. Friendships form and fade. Even routine exists inside a wider motion. On a starship, especially a successful one, too much sameness could become a burden. The ship must remain stable, but human beings do not always thrive in complete sameness. A well-designed mission would need novelty, ritual, beauty, art, privacy, education, celebration, memory, and perhaps even forms of controlled unpredictability, simply to keep the psychological fabric from thinning. In that sense, a starship might need poets almost as much as engineers. Not because poetry powers engines, but because meaning powers endurance. People can survive difficult conditions for astonishing lengths of time if they believe those conditions belong to something meaningful. Without meaning, even comfort can become unbearable. With meaning, hardship sometimes becomes livable. So the question becomes not only whether humans could physically survive a centuries-long mission. It becomes whether they could preserve enough meaning for survival to remain more than mere continuation. And then there is the possibility of shortening the burden through suspended animation, cryosleep, or some future biological slowing of metabolism. Science fiction loves this idea for a reason. It is elegant. Let the ship travel while the body rests. Let the years pass without being felt. Let people depart from one era and awaken in another. It is a beautiful dream. But for now, that is mostly what it is. We can slow metabolism in limited medical contexts. We can preserve certain tissues. We can induce controlled states in some animals that resemble hibernation. But safely placing human beings into long-term suspended states and reviving them without profound damage remains beyond us. And even if such techniques someday become real, they would not solve everything. Someone, or something, still has to run the ship. Systems still need maintenance. Emergencies still happen. A sleeping crew does not remove the civilizational burden completely. It merely redistributes it. This is the pattern that keeps returning. Every apparent solution reveals another layer underneath. Artificial gravity helps the body, but increases engineering demands. Closed ecosystems provide food and air, but create ecological fragility. Generational continuity solves the lifespan problem, but creates cultural and ethical complications. Cryosleep might reduce human stress, but shifts the burden to automation and long-term reliability. There is no single answer waiting quietly in the dark. There is only a set of trade-offs, each asking what kind of human future we are willing to build in order to cross the void. And perhaps that is why the question of leaving the Milky Way becomes so strange. By the time a journey is long enough, hard enough, and artificial enough to make galactic escape even remotely thinkable, we may no longer be imagining ordinary human travel at all. We may be imagining transformed humans, or machine-assisted humans, or cultures so adapted to life inside engineered habitats that Earth-born intuitions no longer fully apply. That does not make the dream impossible, but it does make it more honest. Maybe the question is not simply whether humans can survive the journey. Maybe the real question is which version of humanity could survive it. The version we are now, fragile and deeply earth-bound, may not be enough. A future version, technologically buffered, culturally adapted, perhaps biologically altered, may endure where we cannot. And yet something poignant remains in the older image. The idea that human beings, recognizably like us, with our need for stories and comfort and community and familiar skies, might try to cross the black between stars carrying all of that with them like a small fire in a lantern. There is sadness in that image, but also dignity, because it reminds us that exploration is never only about distance. It is about carrying life into places that were not made for it, and asking whether life can remain itself there. If this gentle journey through the cosmos is helping you unwind, you can quietly leave a like, subscribe, or tell me where you're listening from tonight. I always find it calming to imagine so many different people, in so many different places on Earth, thinking together about what home really means. For now, let one thought settle softly. A future engine might move a human ship. A future civilization might build a closed world. But surviving the journey would require far more than propulsion. It would require preserving bodies, ecosystems, communities, memory, purpose, and the delicate emotional architecture of being human, all while drifting through a darkness that offers no help at all. And that naturally leads to another possibility. If human beings are so difficult to protect over such enormous distances, then perhaps the first travelers to truly move beyond the stars will not be human in the biological sense. Perhaps they will be machines. Perhaps the first things to leave the Milky Way will not breathe, sleep, age, grieve, or long for home in the way we do. And if that is true, then the future of exploration may look very different from the old dream of a crew staring out through a window at another galaxy. That is where the story turns next. Part 8. Could we send machines before humans? If human beings are fragile, machines are patient. That may be the simplest way to begin this part of the story. Not because machines are magical. Not because they solve every problem that space places in front of us. But because many of the hardest questions surrounding long-distance travel become different the moment the traveler no longer needs air, water, sleep, gravity, companionship, or emotional meaning in quite the same way. A machine does not miss home the way a person does. It does not stare at the same corridor for 10 years and feel its mind press against the walls. It does not worry about raising children between the stars. It does not need a garden, a sunrise, a quiet conversation, or the smell of rain. It does not age with the same sadness. It does not ask whether the destination is worth the wait in the way a human heart inevitably would. And because of that, there is a possibility that feels increasingly difficult to ignore. Maybe the first true travelers beyond the deepest limits of human reach will not be us, at least not in the biological sense. Maybe they will be our machines. That idea can sound disappointing at first, especially if what we really want is the old image. A crew on a great vessel. Human eyes watching unfamiliar stars. Human feet stepping onto strange ground. Human voices carrying that ancient mixture of fear and wonder into another world. It is a powerful image. But powerful images are not always the first forms reality chooses. Sometimes the first arrival is smaller, quieter, and less romantic. A probe before a person. A signal before a settlement. a machine before a civilization. In truth, that pattern is already part of our history. Before human beings walked on the moon, machines mapped and tested. Before we landed rovers on Mars, machines orbited it, photographed it, measured it, tasted its thin air in their own limited way. Before any dream of sending people toward the outer planets could be taken seriously, machines went first. They crossed the distances, endured the cold, and sent home what they could. In a sense, machines have always been our first nervous system in the dark. They go where we cannot yet survive. They make the first contact. They return the first rough sketches of places no human body could have reached alone. So when we ask whether humans will ever leave the Milky Way, another question naturally rises beside it. If anyone or anything leaves first, why would it not be a machine? And once that question is asked honestly, the answer begins to lean in one direction. Because nearly every major barrier to human interstellar travel becomes easier, or at least more manageable, when the traveler is mechanical. A machine does not need a pressurized world built around it. It does not need an artificial ecosystem. It does not need years of psychological resilience. It does not need to grow food, raise children, resolve social conflict, or remain emotionally intact while moving through a silence so deep that all messages from Earth arrive years late. It can be smaller, lighter, simpler in some ways, more durable in others. It can tolerate acceleration that would crush a human body. It can endure conditions that would slowly poison living tissue. That does not make the problem easy, but it changes the scale. And changing the scale is sometimes enough to open a frontier. Imagine a tiny probe, no larger than a hand or a book, pushed outward by powerful beams of light from within our solar system. No crew, no cabin, no kitchen, no sleeping quarters, no medical bay, no spinning habitat to imitate gravity. Just instruments, communications, shielding, guidance, and whatever intelligence the craft carries within its circuits. Such a machine might be able to travel much faster than a human vessel ever could, simply because it does not have to preserve a whole living world around itself. That matters enormously, because once the ship becomes smaller, many burdens lighten at once. Less mass means less energy required for acceleration. Less internal complexity means fewer life support failures to worry about. Less concern about radiation to flesh means more freedom to design around electronics rather than biology. The traveler no longer has to be comfortable. It only has to function. And function, in the universe, is often easier than flourishing. This is why so many serious discussions about reaching other stars begin not with human crews, but with robotic probes. Not because people have stopped dreaming of human expansion, but because the cold logic of survival keeps pointing in the same direction. If you want to cross a vast distance sooner rather than later, it is much easier to send something that does not need to remain human all the way through. In some sense, we are already practicing for this future. Voyager 1 and Voyager 2 are not starships, of course, but they are reminders of what machines can do when asked to be patient. They have endured for decades in conditions that would kill a person almost immediately. They have gone farther than any human-built objects ever sent into space. They have continued working long after the era that launched them has faded into history. Their power is dwindling now, and one day they will fall silent. But even their silence will be meaningful. Two crafted things from Earth, still moving outward through the dark long after the hands that built many of their parts are gone. There is something deeply moving about that. Because even without consciousness, even without feelings, a machine can still carry intention. A machine can still be a message. And perhaps that is the first quiet answer to the fear that robotic exploration is somehow less meaningful than human exploration. A machine is not less meaningful simply because it does not feel. What matters is what it carries outward: knowledge, design, memory, evidence that somewhere in the universe, on one world around one star, matter learned to ask questions and then built instruments to carry those questions beyond itself. That is not a small thing. It may, in fact, be one of the most human things we do. Still, there is another layer to this possibility, and it is more complicated. What if future machines do not remain as limited as the probes we know now? What if they become far more autonomous, far more adaptive, perhaps even capable of repairing themselves, building copies of themselves, or making decisions in circumstances too distant for Earth to guide in real time? That is where the idea begins to shift from simple robotics into something more transformative. A machine sent to another star cannot rely on continuous human supervision. The delays are too large. Even a nearby star system is years away by light-speed message. So any serious interstellar probe will need a degree of autonomy much greater than most spacecraft have today. It will need to detect problems, manage resources, navigate uncertainty, prioritize objectives, and perhaps respond to surprises in ways its creators did not specify line by line. That does not necessarily mean consciousness in the human sense, but it does mean independence. And independence changes the emotional meaning of the mission. A probe that simply coasts and transmits is one kind of traveler. A probe that observes, learns, adapts, and perhaps even chooses among possible actions is another. A probe that can repair itself is another again. And a probe that can use local materials at its destination to build new instruments, or even more probes, enters an entirely new category. This is where the dream of machine exploration becomes almost unsettling in its scale. Because if a civilization ever learns to build self-sustaining exploratory systems, then the galaxy may open to those systems long before it opens to biological humans. Not quickly, not in a way that makes distance disappear, but steadily, quietly. A network of machines crossing star systems over thousands or tens of thousands of years, extending observation, memory, and perhaps even industry outward in ways that do not depend on fragile human bodies surviving every leg of the journey. And once you imagine that clearly, another question appears. If those machines are acting on our behalf, does it still count as humanity exploring the stars? There is no perfectly tidy answer. Part of most people wants to say no, that a machine is only a messenger. That the deeper meaning of exploration requires a living witness, a human presence, a body standing there in the dust beneath another sky. And yet another part of the mind hesitates. Because human beings have always used tools to extend themselves. A telescope extends sight. A microphone extends voice. A ship extends the range of the body across water. A rover on Mars is not human, but it is also not wholly separate from human intention. It is a piece of our curiosity operating in a place where our lungs would fail instantly. So where, exactly, do we draw the boundary between us and the instruments through which we explore? Perhaps there is no sharp boundary. Perhaps a machine probe is not the opposite of human exploration, but its first distant form, a kind of remote touch. A mechanical fingertip reaching into darkness too deep for flesh. That idea becomes even more interesting when we consider the possibility that machines might someday carry not just sensors, but versions of human knowledge in richer and richer forms. Not merely photographs and chemical readings, but libraries, languages, maps of our biology, records of our art, memory archives, perhaps even simulations of human thought. A probe could become more than an instrument. It could become a vessel of inheritance. In that case, a machine leaving the Milky Way would not simply be a robot escaping our galaxy. It would be a fragment of Earth carrying its story outward. Not alive in the way we are alive, but not empty, either. There is something strangely comforting in that possibility. Perhaps because it sidesteps the most tragic parts of the old dream. No families condemned to generations in a sealed habitat. No children born into an inherited mission they never chose. No human bodies spending centuries under engineered strain. Instead, small emissaries. Durable, patient, unsentimental, carrying what they can. If they fail, no one suffocates. If they succeed, our horizon widens. And if they continue long after our own civilization changes beyond recognition, then at least some thread of our curiosity remains in motion. Of course, machines come with their own problems. They can fail. They can be damaged by radiation, dust, heat, cold, impact, and simple design limits. Electronics degrade. Software contains errors. Unexpected environments produce strange consequences. A probe that must operate for decades or centuries cannot simply be built well. It must be built with a kind of humility, redundancy, fault tolerance, grace under failure, the ability to continue doing something meaningful even when perfect function is lost. And if we imagine truly advanced machine exploration, especially autonomous or self-replicating systems, then the questions become more serious still. What rules guide them? What prevents drift away from their intended purpose? What ethical boundaries should exist around a machine that can act far beyond human supervision? Would we trust such systems to alter environments, harvest materials, or reproduce themselves in distant star systems? Would we fear them? Would we one day depend on them so heavily that the line between exploration and delegation becomes difficult to see? These are not reasons to reject the idea. They are simply reminders that every path outward carries new forms of responsibility. A machine may solve the biological problem, but it does not solve the moral one. Still, even with those cautions in place, machine exploration remains the most believable first step beyond the limits of human survival. If our goal is simply to know what lies elsewhere, to map, to measure, to witness, to test the possibility of reaching beyond our own local star neighborhood, then machines are almost certainly the way forward. And perhaps, in the very long run, they could do more than that. Imagine a future many centuries from now. Humanity may still be on Earth, or spread through parts of the solar system, perhaps even into nearby stars in some limited way. But ahead of us, farther out, goes a growing frontier of machine travelers. Some are simple probes. Some are observatories. Some may build infrastructure in advance. Some may create relay stations or seed factories. Some may wait, dormant, until another phase of civilization catches up. The galaxy, in this picture, does not open through one great leap. It opens through layers. Biological life expanding carefully where it can. Machine systems ranging farther, faster, enduring more. That feels less like a heroic myth and more like how reality usually unfolds. Messily. Gradually. By means of many overlapping tools rather than one grand solution. And if that is true for the stars, it may also be true for the Milky Way itself. Could machines leave the galaxy before humans do? Very possibly. In fact, if leave is defined literally, then a sufficiently long-lived probe with enough speed might cross beyond the main galactic disk or even travel onward into intergalactic space long before any biological human ever could. Not because machines are superior in every sense, but because they are better matched to certain kinds of distance. They can endure slowness with less suffering. They can survive loneliness without psychological collapse. They can remain dormant without despair. They can treat time almost differently, because they do not experience waiting in the way we do. And that may be the key. The universe is not only a test of intelligence, it is a test of endurance. Human beings are intelligent, yes, but machines may be better at a certain kind of endurance that the cosmos quietly rewards. In that case, the first things from Earth to truly leave the Milky Way may not be human settlers or human crews at all. They may be silent probes, moving outward for ages, carrying data and design, not caring how long the journey lasts because caring is not part of what they are. There is something lonely about that image, but also something noble, because it suggests that even if our bodies remain close to home, our curiosity does not have to. Our curiosity can travel in other forms. And then there is an even deeper possibility, one that blurs the distinction altogether. What if future humans are not entirely biological in the old sense? What if the explorers of deep time are hybrids, or digital minds, or machine-supported persons whose identities can survive in non-biological substrates more easily than flesh ever could? Then the question, machines or humans, stops being clean. The traveler becomes something in between. A continuity of memory and intention carried in forms less vulnerable than the body's evolution gave us on Earth. That possibility is speculative, and it belongs partly to philosophy as much as engineering. But it reveals something important. The farther outward we imagine the journey, the harder it becomes to preserve old categories. Human, machine, traveler, home. These may not remain separate in the future we are considering. And perhaps that is why the topic feels so strange in the quiet hours of night. Because it asks not only whether we can leave the Milky Way, it asks what part of us would do the leaving. Would it be our bodies? Our machines? Our memories? Our descendants, transformed enough that they no longer resemble the human beings who first looked up and wondered? No one knows. But the most grounded answer, for now, is still the simplest one. If anything from Earth reaches the farthest distances first, it will probably be mechanical, smaller than us, colder than us, more patient than us, and maybe, in a sense that matters, still ours. If this calm journey through the cosmos is helping you settle in tonight, you can quietly leave a like, subscribe, or share where you're listening from. I always find it soothing to picture all those different homes on Earth connected by the same long questions. For now, let this thought rest softly in the dark. The first things to leave the Milky Way may not breathe. They may not dream. They may not know they're traveling at all. But they could still carry something unmistakably human with them. Our questions. Our patterns. Our refusal to stay completely still in the face of mystery. And once that possibility is allowed into the story, another question appears almost immediately. If something from Earth ever did leave the Milky Way, where would it actually go? Not in a poetic sense. Not just outward. But toward what? What lies beyond our galaxy that could even count as a destination? That is where the journey turns next. Part 9, if we ever left, where would we go? Once you begin imagining that something from Earth might one day travel beyond the Milky Way, another question rises almost immediately. Toward what? Not just away from here, not just outward, but toward what actual place? It is a strangely calming question, because it forces the imagination to slow down. Until now, leaving the Milky Way may have sounded like a single dramatic act, almost like stepping through a door. But the moment we ask where we would go after that, the universe becomes structured again. The darkness is no longer just darkness. It has geography. It has neighbors. It has islands in the void. And some of those islands are closer than others, though closer, in this part of reality still means distances that make ordinary travel feel very small. So if something from Earth ever truly began moving beyond our galaxy, what would the map ahead look like? The first answer is simple. Mostly emptiness. That may sound disappointing, but it is one of the most important truths in the whole story. Space between galaxies is not crowded. It is not like sailing from one coastline to another across a lively sea. There are no glowing lanes, no convenient stopping points, no chain of busy outposts scattered neatly between the Milky Way and its neighbors. The great spaces between galaxies are thin, dark, and quiet. Intergalactic space is one of the loneliest environments the universe can offer. And yet it is not completely featureless. The Milky Way is not alone. Our galaxy belongs to a small gathering called the Local Group, a gravitational family of galaxies bound together across millions of light years. The two dominant members are the Milky Way and Andromeda, with a third major spiral called Triangulum also part of the group. Around them drift many smaller dwarf galaxies, faint companions moving in slow, ancient patterns, some close, some more distant, all held together by gravity in a dance so slow it almost feels still. That matters because if something were ever to leave the Milky Way, it would not emerge into a totally empty universe right away. It would first enter the wider territory of our local galactic family. In a way, leaving the Milky Way would not mean leaving home all at once. It would mean stepping out of one house and finding that the neighborhood is still there, just spread across distances so large that the word neighborhood starts to feel almost absurd. Still, even absurd neighborhoods have directions. So let us imagine the possibilities. The first destinations beyond the Milky Way would almost certainly not be large, famous galaxies like Andromeda. They would more likely be smaller companions closer to us, the dwarf galaxies that orbit or accompany our own. These are not as grand in the popular imagination, but they may be far more realistic as first external targets simply because they are nearer. The Large Magellanic Cloud is one of the best-known examples. If you live under the southern sky on Earth, it can actually be seen with the naked eye as a misty patch of light. It is a satellite galaxy of the Milky Way, smaller than our own but still rich with stars, gas, and structure. Nearby it is the Small Magellanic Cloud, another companion, smaller still, and also visible from the southern hemisphere under dark skies. There is something lovely about that. Two neighboring galaxies are not only real, they are visible to the unaided human eye. Not reachable, of course, at least not for us, but visible, present, hanging in the dark as reminders that the Milky Way has company. If humanity ever learned to send powerful probes far beyond the galactic disk, galaxies like these might become natural early targets. Not because they are easy, but because they are less impossible than the more famous alternatives. They are nearby by extragalactic standards, still far beyond any casual use of the word near, but within the range where the imagination can at least begin to rest on them. And that is useful, because once a destination can be pictured, it starts to become part of a real map instead of a vague dream. But perhaps the galaxy that most powerfully captures the imagination is not a dwarf companion at all. It is Andromeda. Andromeda is our great neighboring spiral, larger in some ways than the Milky Way, broad and luminous and ancient. On a dark enough night, far from city lights, it can also be seen with the naked eye as a faint smudge, a delicate blur in the sky. That blur is extraordinary. It is not a cloud. It is not a nearby star cluster. It is the combined light of perhaps 1 trillion stars, arriving from a distance of roughly 2.5 million light-years. That sentence alone has a kind of quiet force. When you look at Andromeda, you are seeing another galaxy as it was long before humans existed in anything like their present form. The light reaching your eyes tonight began its journey when our species was still unimaginably far in the future. Entire chapters of Earth's biological history separate us from the moment that light first departed. And still it arrives. There is something deeply soothing about that, perhaps because it makes human urgency feel temporary. The universe does not rush. It shines across millions of years and lets the story unfold slowly. So if something from Earth ever truly left the Milky Way and aimed for a major destination, Andromeda would almost certainly become the symbolic prize. Not because it is practical, but because it is the nearest great spiral. It is the next big city in the cosmic dark, the obvious other shore. And yet even that phrase, the other shore, becomes strange when examined honestly. A shore suggests a crossing, and crossings suggest duration that human minds can emotionally hold. But Andromeda is so far away that the journey, even for imagined future technologies far beyond anything we possess now, remains almost beyond cultural scale. At 1% of the speed of light, a speed already wildly beyond our current human spacecraft for sustained travel, the crossing would still take around 250,000,000 years. That is not a voyage in the human historical sense. That is deep time. That is continental drift. That is the rise and fall of whole biological ages. And that means something important. Even if Andromeda is the nearest great destination beyond the Milky Way, It may not feel like a destination at all to any civilization that remains psychologically similar to us. It may remain a direction rather than a reachable goal, a statement of longing, a horizon that gives shape to the dream without ever becoming a practical itinerary. Still, it would be wrong to say there is nowhere else to go. There is Triangulum, another spiral in the local group, smaller than Andromeda but still a real galaxy with its own stars, clouds, and possible worlds. There are numerous dwarf galaxies scattered around the local group, some close to the Milky Way, some orbiting Andromeda, some harder to classify cleanly in the imagination but no less real. Each one is a candidate, at least in principle, for some future machine emissary, some probe or archive or fragment of Earth trying to step beyond the galactic home it was born in. But beyond the local group, the map becomes colder. The nearest clusters and groups of galaxies beyond our own are much farther away still. The great cosmic web stretches outward in filaments and knots, with galaxies gathering into larger structures, yet separated by vast expanses of thin dark space. At that scale, the idea of choosing a destination begins to feel less like planning and more like philosophy. Because what are you really trying to do at that point? Reach a particular galaxy? Carry information outward as far as possible? Escape? Observe? Survive? Leave a trace? The destination changes depending on the purpose. And this is where the question becomes more interesting than it first appears. If something from Earth were ever to leave the Milky Way, would it really go somewhere specific in the way explorers once sailed toward known shores? Or would it simply move outward, away from home, into intergalactic space, carrying itself until time or failure eventually decided the rest? There is a real possibility that the first true departures from the galaxy, if they ever happen, would look more like that. Not a triumphant arrival at another island of stars, but a long outward drift. A crossing into the dark just to prove that the crossing could be made at all. That sounds melancholy, but it is not necessarily empty. A probe does not need to arrive dramatically in order to mean something. Even crossing the galactic boundary, however that boundary is defined, would itself be a profound event. It would mean that a thing made on Earth had moved from one great structure of the universe into the medium between structures. It would mean that the history of one small planet had extended itself into a region so sparse and remote that almost nothing born of biology has any natural place there. And yet, even in intergalactic space, there would still be destinations ahead, however impossibly far. That is part of what makes the universe so emotionally strange. It is full of things you can point to, measure, and name, while still remaining far beyond anything you can practically visit. There is also another twist here, one that softens the harshness a little. Andromeda is not merely sitting still in the distance. It is moving toward us. In fact, the Milky Way and Andromeda are expected, over billions of years, to approach and eventually merge in a long, slow galactic encounter. This is not a collision in the everyday sense, where stars smash into one another like stones. Space is too empty for that on a large scale. It is more like two immense swarms of stars, gas, dust, dark matter, and gravitational influence gradually interweaving over eons until a new combined structure emerges. That future merger changes the emotional meaning of destination in an odd way. The nearest great galaxy is already on its way here. Slowly, patiently, indifferently. Long after human institutions, nations, languages, and perhaps even species have changed beyond recognition, the Milky Way and Andromeda will draw together. The universe, in its own unhurried way, will reduce one of the distances we find most overwhelming. That does not help us now, of course. No human civilization is going to wait 4 to 5 billion years for a neighboring galaxy to become more accessible. But it does offer a perspective worth resting in. Some of the destinations we imagine reaching are not fixed forever. The cosmos itself evolves. Structures move. Boundaries shift. Home is not static. And that matters because it reminds us that asking, "Where would we go?" is partly a question about when as well as where. A destination that is unreachable now may look different in another cosmic age. Still, from our present moment, the practical answer remains clear. If anything from Earth leaves the Milky Way in the foreseeable future, it would likely do so in one of three ways. First, it could head toward a nearby dwarf companion, treating that smaller galaxy as the first external frontier. Second, it could head more symbolically toward Andromeda or another major local group target, even if the true crossing would belong to unimaginably long timescales. Third, it could simply head outward into intergalactic space itself, not because empty darkness is a satisfying destination, but because the act of leaving would be the point. That third option is worth sitting with, because it reveals something almost philosophical about human curiosity. Sometimes the destination is not a place. Sometimes the destination is a threshold. The first people who crossed oceans did not always know exactly what waited on the far side. The first climbers of unknown peaks, the first navigators of deserts, the first astronauts leaving Earth's atmosphere, all of them in some sense were moving toward a boundary rather than a fully understood arrival. To cross was to learn. To cross was to change the map. Leaving the Milky Way, if it ever happens, may begin in that spirit. Not because the void is attractive in itself, but because once a threshold exists, some part of the human mind wants to know what it feels like on the other side. And yet there is another layer here, perhaps the quietest one. What if the deeper truth is that there is nowhere better to go? Not nowhere else. Nowhere better. The Milky Way is not a cramped box we are desperate to escape. It is an enormous spiral city of stars, with more room, more worlds, more mystery, and more possible futures than any civilization could exhaust for ages beyond counting. If a mature humanity ever becomes interstellar, it may discover that the galaxy itself is already effectively infinite for practical and emotional purposes. There may be no urgent reason to leave at all. Not because the dream was false, but because home turned out to be larger than the dream assumed. That is a beautiful possibility. It suggests that the desire to leave the Milky Way may belong more to our present smallness than to our future maturity. Right now, the galaxy feels like a boundary because we cannot move freely within it. But if we ever could, the boundary might soften. The question might change from, "How do we escape?" to, "How do we belong responsibly within something so vast?" That would be a very different kind of civilization, less obsessed with the next dramatic leap, more patient with scale, more at peace with the possibility that not every horizon must be crossed in order to have meaning. And still, even such a civilization would probably continue sending something outward. Probes, archives, machines, signals. Not because it needed to flee, but because curiosity does not fully rest. Even a species content with its home may want to let a few questions travel farther than it can. Perhaps that is the gentlest version of the future. Not an empire racing from galaxy to galaxy, but a civilization deeply rooted in one galaxy, occasionally extending careful instruments into the darkness beyond, more as acts of wonder than conquest. That future feels more believable than many of the louder fantasies. It also feels more human, not because it is timid, but because it understands proportion. The space beyond the Milky Way is real. Its destinations are real. The dwarf galaxies, Andromeda, Triangulum, the local group, the larger web of structure stretching beyond all of them, all of it exists whether we ever reach it or not. The universe does not become less beautiful because some of its shores remain too far away for us to touch directly. In a strange way, it may become more beautiful. Because beauty is not always something to be possessed. Sometimes it is something to be beheld, carefully, from a distance that teaches humility. And perhaps that is what Andromeda has always been. Not merely a target, a lesson. A faint blur in the night, just visible enough to awaken longing, just distant enough to remind us that longing does not guarantee arrival. If this slow journey through the cosmos is helping you unwind tonight, you can quietly leave a like, subscribe, or tell me where you're listening from. I always enjoy imagining all those different places on Earth connected by the same sky and the same questions. For now, let one thought settle softly. If something from Earth ever left the Milky Way, it would not find a busy road waiting outside. It would find darkness, great distances, and a few far islands of stars. A dwarf galaxy, perhaps. Andromeda, maybe, as a dream more than a near destination. Or simply the open void itself, crossed for the sake of knowing that crossing was possible. And that brings us to the final question. After all the distance, all the engines, all the human limits, all the machine possibilities, and all the destinations that may forever remain farther than comfort can bear, what is the real answer? Will humans ever leave the Milky Way? Not in fantasy, not in metaphor, but honestly. That is where the story comes to rest. Part 10, The Real Answer. Will humans ever leave the Milky Way? So after all of this, after the distance, the speed, the fuel, the long silence between stars, the fragility of the human body, the patience of machines, and the few faint destinations waiting beyond our galaxy, we arrive at the quiet center of the question. Will humans ever leave the Milky Way? The honest answer is not a clean yes. It is not a clean no either. It is something softer than that, something more human. If by humans we mean people very much like us, biological human beings with ordinary lifespans, ordinary bodies, ordinary emotional needs, traveling in ships that still feel recognizably like ships, then the answer is probably no, at least not in any future close enough for us to imagine comfortably. The distances are too large, the timescales too severe, and the cost too extreme. Even leaving the main disk of the Milky Way would require a journey so long and so difficult that it would strain the meaning of travel itself. Reaching another major galaxy would push the problem even farther, into spans of time so immense that civilization, memory, and identity would all begin to blur. That is the answer most people do not want at first. Because we are used to stories where the frontier gives way eventually. We expect difficulty. Yes, we expect sacrifice. But we also expect a path. Build the better ship. Discover the better engine. Wait long enough. Be brave enough. The universe will open. And maybe part of it will. But not necessarily in the form our instincts prefer. Because the Milky Way is not a fence around a field. It is not a nearby mountain range waiting for the right road. It is an enormous galactic home, so wide and so full of stars that even imagining its edge already pushes human thought close to its natural limit. To leave it is not like leaving a country. It is more like trying to leave an entire world of worlds. And perhaps that is why the question feels so heavy at night. It asks whether the human instinct to keep going eventually reaches a point where physics no longer bends to courage. Not because courage is meaningless, but because courage is not the only thing that decides what can be crossed. Still, the deeper and calmer answer is more interesting than a simple no. Because if by humans we mean the longer story of humanity, including the tools we build, the minds we may one day shape, the descendants we may become, and the machine extensions through which our curiosity might continue traveling long after our present bodies cannot, then the answer becomes more open. Then, in a very long future, something that still belongs to the human story could leave the Milky Way. Not tomorrow. Not soon. Not in the age of our children, or perhaps even of our species in its present form. But someday, through machines, through patient probes, through hybrid forms of intelligence, through civilizations more adapted to deep time than we are now, something that began on Earth may continue outward into intergalactic space. That is a different kind of answer. Less cinematic, less emotional in the immediate sense, and yet, in another way, even more profound. Because it suggests that the question was never only about bodies crossing a line in space. It was about whether our curiosity, our pattern of wondering, our refusal to let the horizon remain entirely untouched, might someday extend beyond the galaxy that made us. And to that, the answer may be yes. But even that yes comes with a necessary stillness around it. Because sometimes when people imagine leaving the Milky Way, what they really imagine is freedom, escape, a kind of final victory over scale itself. As if getting beyond our galaxy would prove that no home can contain us for long. As if a species becomes fully grown only when it steps beyond the structure that birthed it. But there is another way to see it. Maybe leaving the Milky Way is not the great proof of maturity. Maybe learning to understand what the Milky Way already is would be enough. The galaxy contains hundreds of billions of stars. Around many of those stars are planets. Around some of those planets may be oceans, storms, ice, deep underground chemistry, perhaps even life. The galaxy is not a cramped place we have already outgrown. It is so huge that a civilization could spend ages beyond counting simply trying to know a small corner of it. Even if humans someday become truly interstellar, spreading carefully from one star system to another, building outposts, observatories, archives, habitats, slow roads of knowledge between distant suns, the Milky Way would still remain more than enough for dreams, more than enough for mystery, more than enough for history. So perhaps the real answer to the question contains a quiet reversal. It may be that humans do not need to leave the Milky Way in order to become a vast civilization. It may be that the Milky Way itself is already the vast civilization waiting to happen. That changes the emotional texture of the whole subject. Because if leaving the galaxy is not necessary for meaning, then failure to leave is not a kind of defeat. It is just a recognition of scale. A recognition that home is larger than the instinct to escape first assumed. There is dignity in that. A mountain is not diminished because you do not reach the next mountain beyond it. An ocean is not disappointing because you never sail past every shore. And the Milky Way is not a prison merely because another galaxy lies too far away for ordinary human bodies to reach. It may simply be home on a scale so large that we mistook it for a boundary. That may be one of the softest truths in this whole journey. Home and boundary are not always opposites. Sometimes a boundary only feels restrictive because we have not yet learned how vast the home within it really is. Still, there is a reason the question continues to pull at the imagination. Because human beings have always looked beyond the current frame. A child looks beyond the door. A sailor looks beyond the horizon. A physicist looks beyond the known law. A species looks beyond the world that raised it. This instinct is not a defect. It is one of the engines of knowledge itself. Without it, there would be no telescopes, no rockets, no probes, no maps of distant galaxies, no nights spent asking whether the dark beyond our own star means anything at all. So it is natural that some part of us wants a clear answer that feels like victory. Yes, someday, we will leave. Yes, the line will be crossed. Yes, the galaxy will become just another chapter. But the universe does not always offer answers in the emotional shape we want. Sometimes it gives something more subtle. Sometimes it says that the frontier is real, but not for you in the way you first imagined. Sometimes it says your tools may go farther than your body. Sometimes it says your descendants may become something different enough that the question must be asked again in new language. Sometimes it says that understanding the scale of what cannot be done is part of wisdom too. And perhaps wisdom is the better final mood for this question than triumph. Wisdom says this: biological humans are creatures of Earth. We are made of a planetary history. Our lungs, bones, nervous systems, circadian rhythms, emotional architecture, all of it was shaped beneath one atmosphere, one gravity, one star. To ask whether those creatures can casually leave a galaxy is like asking whether a fish can casually cross a desert. With sufficient technology, perhaps something like the fish can be protected, transformed, carried. But the difficulty is not incidental. It goes all the way down into the form of the creature itself. That is why the problem is so large. Not because we are weak, but because we are deeply specific. We belong to a certain kind of world, and galaxies are not built to care about that belonging. At the same time, wisdom also says this: humanity has a strange gift for extending itself beyond the limits of the body that first asked the question. We build telescopes to see farther than eyes can see. We build submarines to survive where lungs cannot. We build satellites to rise where flesh alone would fall. We build probes to touch places that would kill us instantly. Every great extension of human reach has involved tools that first looked unnatural, impossible, or emotionally unsatisfying compared to the older dream of going there ourselves. And yet those tools mattered. They mattered because they were still us, in a certain important sense. Not as completely. Not substitutes for lived presence, but extensions of intention. Extensions of wonder. Extensions of the part of the human story that does not like to leave mystery entirely untouched. So maybe the question should not end as a test of pride. Maybe it should end as a test of honesty. Will humans ever leave the Milky Way? Probably not as ordinary human travelers. Possibly as machine-guided descendants, hybrid minds, or long-lived emissaries of a civilization transformed by deep time. Very likely, if it happens at all, through something quieter and stranger than the old dream of a heroic crew looking out from a shining window. That is not less beautiful. It is just less comforting to the version of us that wants the universe to behave like a story built around our current form. And perhaps there is one more truth beneath even that. The desire to leave the Milky Way may come partly from a misunderstanding of what greatness looks like. We often imagine greatness as expansion without limit, more reach, more territory, more distance crossed. But the cosmos offers another version. Greatness may also be the ability to understand one's place without needing to dominate every farther horizon. To know the scale of the galaxy and feel awe rather than frustration. To accept that some things may remain beyond bodily reach while still allowing them to enlarge the mind. That kind of greatness is quieter, but it may be closer to what the universe actually invites from us. Not conquest, not ownership, attention, patience, wonder disciplined by reality. There is something restful in that, especially late at night, because it means the question does not have to end in disappointment. It can end in proportion. The stars beyond the Milky Way do not become meaningless if we never stand beneath them. Andromeda does not lose its beauty because it remains a distant blur. Intergalactic space does not become wasted simply because no human heartbeat may ever cross it. Some things are valuable not because they will be possessed, but because they reveal the scale of being alive in a universe where possession is not the final measure of meaning. When you look up at the night sky, you are already inside something astonishing. That may be the most important thing to remember. You are not standing outside the universe wondering whether it contains wonder. You are already within one of its great structures. A spiral galaxy full of ancient light, moving stars, hidden planets, drifting clouds, black holes, old explosions, future suns, and possibilities still untouched. The desire to leave it is understandable. But perhaps the first responsibility is simply to notice where you already are. And if humans do someday leave, if some far future branch of our story sends patient machines or transformed descendants beyond the galactic edge, then that act will likely mean the most not because it proves we escaped, but because it proves something gentler. That we remained curious long enough. That across war, grief, change, forgetting, rebuilding, and the small noise of ordinary history, some thread of attention held. Some line of inheritance stayed alive. Some species, born on one wet planet around one ordinary star, kept asking questions for such a long time that eventually even the Milky Way was not the end of the road. That would be extraordinary. But so is this moment. So is being the kind of creature that can ask the question at all. That too deserves more reverence than it usually gets. A mouse does not ask about Andromeda. A stone does not wonder whether it will ever leave its galaxy. Matter became life, and life became thought, And thought became the kind of quiet presence that can lie awake under a ceiling, or under a blanket, or by a window, and imagine the edge of the Milky Way. Even if no human ever crosses that edge in person, the fact that the question can exist is already a kind of miracle, if that word is used gently. And maybe that is the final place where the story comes to rest. Not in certainty, not in a triumphant promise, but in a calm answer that leaves room for both limitation and wonder. Will humans ever leave the Milky Way? Probably not in the ordinary way people imagine. Maybe, one day, through tools, descendants, or forms of travel that would seem strange to us now. But whether we do or not, the larger truth remains. The Milky Way is not a small enclosure keeping us from a bigger life. It is already one of the great theaters of existence. Already vast enough to humble us. Already rich enough to absorb dreams for ages. Already beautiful enough that learning how to belong within it may be the greater challenge than escaping it. And perhaps that is not a disappointing ending after all. Perhaps it is a peaceful one. Because there is relief in realizing that the universe does not require us to go everywhere in order for our lives to matter. There is relief in knowing that wonder is not postponed until the next galaxy. It is here already, folded into the dark above your roof, your town, your sleeping world. It is here in the old light of stars. Here in the silent band of the Milky Way crossing the sky. Here in the fact that you can think about distances your body will never travel and still feel enlarged by them rather than diminished. That may be enough. More than enough, really. And if you have enjoyed drifting through these questions tonight, you can quietly leave a like, subscribe, or share where in the world you're listening from. I always find it comforting to picture so many different people on Earth, under the same galaxy, meeting each other for a moment in thought. For now, let the final answer settle softly. Humans may never leave the Milky Way as ordinary travelers of flesh and bone. But the human story may still reach farther than the body can. And even if it never does, we are already living inside a cosmos large enough to spend a lifetime, and perhaps a civilization, learning how to love. So as the night deepens, and the questions grow quieter, perhaps the most peaceful thing to remember is this. We were never standing outside the wonder, waiting to enter it. We were inside it all along.